So, in case you guys didn't know, this is our introduction to vehicle physics, as well as a little bit more. Um, I'm Ross Benz. I'm the sub-team lead for the strategy and VD team. Uh, I've been on the team for, what, 2 years this year? I wasn't on the team last year, but I was helping out. And then I was on the team for SR2, 3, and 4, so a long time ago. But I'm back from a master's, so I figured I would help out a little bit.
My name's Arash, for you guys who don't know me. I'm not an engineer and I don't play one on TV, but I'm here to teach you about vehicle dynamics. I'm starting my 5th year on the team. I did 3 years doing aerodynamics and then 1 year doing a bunch of everything, and then now trying to learn a little bit more about VD.
So to start off, I'd like to say thanks to a few people that helped us put these slides together: Joey, Akash, JJ, and Kai. And then we have a quote down here. We broke something. I think it was traction. We'll be talking about traction a lot, so let's get started.
And just to reiterate on what Ross said, ask questions if you don't get something.
Well, there's a slide about it. So we'll be going through an introduction, like a baseline of what we're talking about and next steps. And then we'll be talking a lot about tires, and then we'll slip into vehicle dynamics. And hopefully you guys will be asking questions the whole way. So like I said, interrupt me anytime if you have a question. It's not a problem. If you feel comfortable, if you could say your name and like your major and what year you are. If you don't feel comfortable, don't bother, just ask the question. If you're not speaking, please mute so we don't have any weird noises. And then it just continues on. Basically, don't feel bad about asking questions. It doesn't matter if you think it's stupid. Other people probably have the same question or need clarification as well. So again, I can't say this enough. Ask questions. So as a baseline, what is the goal of a racer or race car? It's not to turn dollars into decibels. It's not necessary to look fast or to look pretty. Do we want to go as fast as possible? Maybe. Do we want to have the lowest times possible? Maybe. Which is kind of the same thing as having the highest average speed. Usually we want to get as many points as possible, but the end goal is to win. So however the rules for the series are written, we want to win. For our series, it's not just about going as fast as possible. There's also static events, but they're a lower weighted score. But we have to juggle and balance between different dynamic events as well as the static events to win overall. How do we achieve the goal of going fast, since that is the primary goal in the dynamic events? Depending on the event, being fast is different things. But for the most part, we want to accelerate as fast as possible, turn as hard as possible, and brake as late as possible. Braking late being to brake as hard as possible, just not for very long. So what do all those things have in common? Well, they're all accelerations in terms of physics. So what we want to do then is maximize those accelerations. So Newton has some laws that can help us figure out how to maximize those accelerations, which in turn, if we keep stepping back, will make the car faster, right? Which allows us to get as many points as possible, which allows us to win, because at the end of the day, that's what we're trying to do. Did we skip this? Oh yeah, we skipped a slide. Okay, so how do we take that to the next step? So Newton's laws, first law, objects at rest will stay at rest. You guys should all know these from high school physics. At rest in this case means in your local frame of reference. So if you're sitting in your car going 60 miles an hour, you are at rest with respect to the car. F equals ma, or force is mass times acceleration. But since we're trying to maximize accelerations, it's easier to think of in terms of accelerations are equal to force divided by mass. So what we can immediately see is if we want to maximize accelerations, we need to up the force or lower the mass, or both. And then actions have equal and opposite reactions. What this means is basically if you want to produce a force, or you can produce a force, but it won't do anything unless some force reacts against it to push you, right? So if I push against the wall pushes back with the same amount of force, right? So what does this mean for us? Well, we have very few things that we can push against. We can push against the ground, we can push against the air, and we can eject or accrete mass. So basically have a rocket eject mass, or like a snow plow building up snow in front of it would be accreting mass, which isn't really practical. So for us, the most practical thing to do is to push against the ground. And we only have 4 ways to push against the ground. And they're all tires, all 4 of them. And they're one of the best ways for us to do it because they produce high forces, and they're efficient at producing force. And what I mean by that is, like, if we want to produce a lateral force, they don't produce a lot of drag force necessarily to do that. So we don't have to then produce even more longitudinal force to overcome drag. So as a quick recap of the initial physics, physics can help us kind of settle down to what we really need to do to win. And how do we win? Well, we get points, we get low times by making lots of acceleration, which in turn happens by making lots of force and or reducing mass. So the way we produce forces is through the tires, through most of the forces anyway. So at the end of the day, every sub-team from VD to aero to chassis, powertrain, we all serve the tires. Or we serve the driver, make it easier for the driver to serve the tires. Any questions? Please ask questions if you have any. All right. So,
how about consistency?
What do you mean by consistency?
You have a well-built car that is not consistent.
So you mean like breaking down?
Yeah.
Yeah, so that is also a factor here. That's much harder to quantify though. But yes, so in order to finish first you must finish, right?
Right.
That is definitely something to be aware of, in that if we talk about risk management, we need to produce as high forces as possible, go as fast as possible, whatever, while still balancing our risk. So if something is going to be very high odds of breaking, it may not be worth doing because it would end up causing us a massive loss of points potentially, right? So that is definitely something that is good to think about when we're designing things. Thank you for bringing it up. Anybody else? Okay, so we've established that everything comes through the tires pretty much. So let's talk a bit about tires. How do tires produce the forces that we so value? Well, first of all, how do we push against the ground, right? We are not have a Fred Flintstone vehicle, so we don't drive it with our feet. And tires are the only way we contact the ground. So we produce all the forces with the tires. How do we get the most forces out of the tires? Well, let's think about how tires work. So the traditional, what you learn in school, definition of friction is equal to mu times normal load. And normal load is the vertical load down on the tire, in this case, or on the object against another surface. So if you push down on a brick on the table, it produces, you have a normal load times its mu, and that allows you to push sideways a certain amount before it starts to slide. So what are the laws governing this? Well, when an object is moving, the friction is proportional and perpendicular to the normal force. So what that means is the brick, if we have a brick sitting on the table and we put a normal load on it, we're allowed to push perpendicular. We can put that perpendicular force on it, right? Proportional in this case means if I increase the normal load, if I double the normal load, I'm allowed to double the side load before it starts slipping. And that is something that is not true for tires. So I would call it semi-valid. Perpendicularity is still true, but proportionality is not true for tires. Friction is independent of the area of contact, so long as there is an area of contact. So what that means is if I have a brick that's half the size of my other brick, and I have the same normal load on them, they will have the same amount of friction or side force before they slide. That is also not true for tires. Tires do care about how much surface area they have in contact with the ground. to produce certain amounts of normal load or lateral load, because in this case for tires, it changes the mu. The coefficient of static friction is slightly greater than the coefficient of kinetic friction. So what this means is if you have your brick sitting on the table and you push on it and it's not moving, eventually when you start it moving, and you can, if you've ever like moved in your house, so you have like a box full of shit and you're trying to like slide it. It takes a lot of force to get it moving, but once you get it moving, the force goes down and you can continue to push it, right? That's because the static friction is higher than the kinetic friction. So once you got it moving, the friction went down and it's much easier to keep it moving. So for tires, this is also true, but the kinetic friction tends to be quite a bit lower than the static friction. So we want to try and keep them in static friction. And then within rather large limits, kinetic friction is independent of velocity. So what that means is that box, once you got it moving, it doesn't matter if you could run at 60 miles an hour or if you're pushing it at like 1 mile an hour, the kinetic friction is going to be roughly the same. And this is pretty much true for tires as well. And then the big one is friction is dependent upon the nature of surfaces in contact. So if the tire is rolling around on gravel versus on a road, you can have different levels of friction. Or if we're driving on ice or snow, the friction is going to be really low. And the reason that tires are so much more complicated than the friction we talk about in high school physics or even college physics for the most part is because they're soft. They're not, the friction equations we learn in school are for things that are infinitely rigid or assumed infinitely rigid. So because tires are soft, they have additional complexity that isn't modeled in the normal equations. And because they're so complicated in engineering, we try to simplify them by talking about a couple of different things that allow us to simplify the way we work with the tire so that we don't have to worry about what's going on in the background. We just ask, you know, if I turn the tire this much, how hard does it push? Or if I spin the tire faster, how hard does it push? We don't really try to worry about what's going on between the contact patch and the deflection into the asphalt. That's too complicated for what we're trying to do. Any questions? Okay, so what are those things that we are concerned with as far as a tire goes to simplify in engineering terms what we're doing? Well, so there's two things that we use to generalize tire behavior: slip angle and slip ratio. And I'm going to explain them for you. So slip angle is the top picture here. And we have a tire was going straight, and straight being dead vertical in the image. And then we turned it some angle, right? And what that does is it deflects the rubber. So if you have a tire and you just pushed it down on the road and then you turned it, then the rubber that was first contacting the road would still be pointing the direction it was pointing, even though you just turned the tire, right? Because that stuff's stuck to the road. So that produces a torque, right? Trying to put it back where it was. But if you roll it forward, it also produces a lateral force. So this is how the car turns, because of this lateral force. And then conversely, in the longitudinal direction, we have something called slip ratio, which you can see in this GIF. This is a top fuel dragster accelerating. And what happens is if we take that same tire and we push it against the ground again, and then we try to torque it forward, the contact patch stays stuck to the ground, but the whole tire stretches, right? So we stretch the rubber behind the contact patch and we compress the rubber in front of the contact patch. And this produces longitudinal force, which drives the car forward. And you can see that in this GIF. There's so much stretch that it's starting to crumple the walls of the tire because this is a drag car that's producing thousands of horsepower. Does this make sense to everybody? Because it's only going to get more complicated.
Yeah, this stuff's pretty important. So if there's any questions or clarifications, definitely ask right now. So I think one of the key points is that tires are flexible, and they also have a fair amount of friction. So when you load them, the part contacting the ground gets stuck, and then you're basically twisting the tire around that part, or like warping it, and all the forces come from the tire trying to spring back to being straight, whether that's forward or back or side to side.
Mm-hmm. No questions? Okay. Parts. Oh, well, that's interesting. Reload.
Oh no.
Hold on. That was weird. Oh, we got chat questions.
Oh, good.
Never mind.
Oh. I guess while Ross is getting that, do you guys think tires are kinetic or static friction when you're driving around?
It's weird.
Are they kinetic?
As in regular driving, why do you think?
Oh, because they're moving. And let's see. Oh, friction, static
Yeah.
friction.
Well, so they are moving, but
Yes.
it depends on your frame of reference. We talked about things at rest, right? So
Oh yeah, so the tire and the rim should be the same, but like that GIF you showed, they're stretching and they're moving sometimes. So
the tire piece, the piece of tire that's in contact with the road, is it moving with respect to the road?
I don't understand what you mean. So it's moving with respect to the road.
So think about the difference between something rolling and something sliding.
Oh, right. So when you're going through a turn, there probably is some slipping. And then
So
even when you accelerate or decelerate, it's not going to be exact. Like you couldn't count on it like a gear. Is that what you mean?
If you lock the tires, if you hit the brakes and you have no ABS? Well, first of all, can you guys see my screen again?
Yeah.
Yeah.
Okay, cool. So if you lock the tires, do you think they're in static or kinetic friction?
That would be, if you lock the tires, I think you're in static. And my guess, and you can tell me if I'm wrong, is that from my understanding, if you got like 100% steering, then you got 0 braking and vice versa. If you lock them up, you can't steer any longer.
Well, so let's just stick with, no, forget steering for now. Let's just talk about straight line. So if I'm going 60 miles an hour and I Arnold Schwarzenegger the brakes and they lock up, the tires are going 0 miles an hour now, right?
Yeah.
But but the car is still going 60 miles an hour, let's say.
Right.
So the tire is moving 60 miles an hour, right? It's just not spinning, but it's still moving 60 miles an hour with the car, right?
Oh, so then it's kinetic.
But the road is moving 0 miles an hour. It's not, it's the earth, right?
Okay, so then it's kinetic.
We have a relative
Exactly.
motion.
Yeah, that's
But when the
kinetic.
tire is spinning, right, then it's moving the same speed as the ground when it's in
Oh,
contact.
and that makes it static?
Exactly.
Yes,
Exactly.
It's
That's a very good
counterintuitive.
question. Yeah, I know it is.
It
Yeah,
is.
I know it is. So that's a really
cool.
good question.
I like that. That was good.
So this is where we get in. So if you do a burnout, right? So if let's say you're trying to accelerate the car, do you think that it's faster to do a burnout or to not do a burnout?
I mean, instinctually, I'll just say I don't think it's good to do a burnout because you're losing grip.
Yes, because kinetic friction has lower mu than static friction.
Oh, like going back to moving the box on the table again.
Exactly. Yep.
There you go. So once you
question.
break contact, you have dropped your ability to make traction.
You still make traction, just less.
Okay? And then as a definition, that's so kinetic has less than static. Is that right?
That's almost always true. Yes.
Wow.
Of any materials, almost any material.
That's so counterintuitive. Just thinking about the definitions. Yeah, I like that clarification. Thanks.
But yeah, thank you for being willing to state an answer.
Oh yeah, it's okay. I don't mind learning stuff. I don't know everything.
No. I'm glad, but I would like everyone else here to be willing to put themselves out there and ask questions and answer questions as well. That's all I'm trying to say.
Oh, no problem.
Because you learn a lot more by being wrong.
Yes. It's basically I learned everything.
So now everybody understands that the tire in normal operation is in static friction with the road. They are both stuck to each other unless the car is sliding in some way, whether it's locked brakes or doing a burnout or understeering or oversteering, drifting, right? Drifting would be kinetic friction as well for the rear tires.
If you're turning and your tire assumes a slip angle, does that put us in kinetic?
So the slip angle is the angle between the tire rubber that is touching the road and the rest of the tire, the bulk of the tire. So there's some stretching going on there, but the contact patch that is touching the road, in most cases, I'm not going to try not to use absolutes because there are situations where it's not true. The contact patch that's touching the road will be in static friction with the road.
Yes, and you can think of it as that being the reason why you get a slip angle anyway.
Yeah.
Is because the contact patch is in static friction. It's not sliding with respect to the road, but you're trying to twist the tire. So that's why you have that distortion in the tire. And that's why you end up with a slip angle.
And if we get a little more complicated, that's why let's say your car would understeer, right? You turn the wheel really hard. What ends up happening is you break into kinetic friction. So the slip angle goes to near zero because it's now sliding across the surface. And then in order to get grip back, you actually have to turn the wheel back pretty far because you have to force the tire to get back to stuck before you can start turning again to try and make force.
Ross, I think there's some questions for you guys on the
in the chat.
Yeah. If you can't access it, I can read it for
17
you.
questions. Yeah, if you could read them.
He's asking about slip angle and Aaron's asking about slip angle and lateral force. I should probably have the chat open while we're talking.
Yeah, if you could open it. I can't open it for some reason.
I got it.
Okay.
So
Yeah.
You want to just read it, Cass or Arash?
Aaron's
Or
asking a
Arash,
question, which we have the answer to on the next slide.
Oh, okay. Are there any questions we don't have the answer to on the next slide?
I got a question that you might cover it in the future.
That's fine.
I guess the next question I guess I would have would be, how to determine, do you want a softer tire or a harder tire or one that stretches or one that doesn't, and how do you determine that?
That's a great question.
Slide. That's a good question. All right. Any
Can I
other
ask a question?
Yeah, of course.
Yeah, go ahead.
Okay, so in the case of drifting, when you have your rear tire slipping, because it's kinetic friction, does it have any, does it propel the car forward at all due to the friction, or is it just rubbing the tire and scraping off?
Kinetic friction, you can still produce forces. They're just lower. So yes, like if you imagine doing a burnout, you'll still move forward, just not as efficiently, right? So if you're drifting and you're like pinned on the gas, the car will still be producing longitudinal force.
Is it actually okay?
Hi, this is Fred. So I just want to add something. Tell me if I'm not correct. So everything we've been talking about is based on the assumption that the tire contact patch is single element. So it's either in static or dynamic. But in actual cases, the whole contact patch has infinite rubber elements. So some of them could be in static even when the car is sliding. Some of them could be in dynamic when the car is rolling.
Yeah.
Is that correct?
I think let me go forward a slide and I can explain that a little bit better. But yeah, you're correct. The tire, since it's stretchy and rubber, can be like, say, half the contact patch could be stuck and half of it could be sliding at the same time. Or all of it could be sliding or all of it could be static. Yeah, it's a very complicated device or surface. But you're 100% right. It doesn't have to be all static or all kinetic. For most tires, especially the racing tires we run, there is not a very steep, instantaneous, like, okay, you're in static friction, goes to shit, you're in kinetic friction. It's a very slow roll off as some of the rubber starts to slip and some of it is still stuck to the surface. Thank you for bringing that up.
Yeah, that's a great point.
Okay, so, and the easy way to see it is on this left graph here. So,
you didn't change your slide, I don't think.
Oh, did it not
Yeah,
update?
Yeah.
So you're
Also,
not seeing graphs?
No.
Ah, sheesh.
I'm also not seeing you in present mode.
Can you see now?
Yeah.
Yeah.
Okay, cool. So here's our graphs. So when we talk about tires, it's a lot easier to simplify things into graphs. Lots and lots of graphs. And even then it's still complicated. So let's start with the top middle graph, the driving force graph. So this is me talking about doing a burnout, right? So if you're trying to accelerate the car, you can have a differential speed between the tire's rotational speed and the speed of let's say the speed that the top of the tire is moving linearly versus the ground speed or the speed that the vehicle is moving of like 25%, right? And that'll give you the most longitudinal force. And if you go any higher, it starts to drop off. We start to get into kinetic friction, right? And then by the time we get to like 75% slip ratio, or the difference in those two speeds, it's purely kinetic. The tire's just doing a burnout. And then, as we said before, once you're in kinetic friction, it doesn't really matter how fast you spin the tire. The mu is the same, right? Does that make sense to everybody? And then for braking, if we lock the wheels, it's kind of the same thing, but we can't get over 100% slip ratio because locked is locked. We don't drive the wheels backwards, right? So this is basically a stretched out version of the driving slip graph. It's just stretched so that it's not goes to 200, it only goes to 100%. But for the most part, the tire will behave the same whether you're accelerating or braking, because they're both the same thing, they're just in different directions. For turning, though, it's a bit more complicated. So tire construction and tire rubber will change the way that the tire produces forces as a function of turning or slip angle, is what we're talking about. So we can view this in terms of different tires, which is kind of what we have in this graph. So I'll just ask a general question if someone wants to possibly be right or possibly be wrong. Which of these three colored tires would you rather have on a race car? And why? Why is more important? What?
The blue one.
Okay, so the blue one's better than the green one, I'll agree with you, but I would probably take the red one. And the reason I'm going to say that is because even though its lateral force ability is lower, it's much easier to drive. So if the driver isn't perfect with the steering wheel and doesn't put the car at the exact right slip angle, they have this nice like wide window at the top of the graph where they can the car will perform, and they don't have to be perfect, right? Whereas for the blue tire, if they're not here, they're going to fall off drastically, right? So I would probably choose the red tire. And we run bias ply tires, which is the red tire. I don't even think they make radial tires for our kind of racing. And almost all racing tires are bias ply tires, largely for that reason as well. Because they are much easier to drive. But that was kind of a trick question, so thank you for putting yourself out there. But we can see here how different tires behave. And this is also gets back to what someone was saying before about static versus kinetic friction. So especially the bias ply, right? It stays static for a long time at its peak before it starts to go into kinetic friction and drop off. But even then, this drop off isn't super steep. It's not like, right? It drops off slowly as part of the contact patch goes into kinetic friction while the other part of it is still in static friction. But this is kind of, like I said before, the game we play with, we try to serve the tires and sometimes we try to serve the driver so that they can serve the tires better. I don't know if that makes any sense to people. And then there's the green tires, which are just shitty street tires. So we've been, any questions?
Hey, Ross, can you hear me?
Yeah.
So when designing a race car, do we design from the tires up or from the driver up?
For the most, that's a good question.
Yeah.
So it's kind of a mixture of the two. So we can theoretically design a car that performs, you know, around the tires only, but it might be undrivable, right? It might be so unstable that it's very difficult for the driver to perform. And what we mean by perform in this case, again, is the driver serves the tires. So if we can make it so that it's easier for the driver to stay in this window or to stay in this window or this window, then they at the end of the day will go faster than, so maybe when we design something for the driver, this curve changes and now it only goes like this, right?
Right.
But if it makes it so the driver will always be at the peak, then we may end up going faster, right? Because it's easier to drive. So it's kind of this game we have to play between making the car easy to drive and maximizing the available forces we can produce out of the tires.
Okay,
because if the driver can make the tires produce more force reliably, we may go faster than if the driver can occasionally produce a huge amount of force. But the rest of the time, it's really hard to drive. So that's a good question.
Yeah, that brings up a really good point, especially when we focus on the topic of winning so much. And most, if not all of us, are engineering students. So we always try and like optimize everything or look at things as like numbers on paper. And we're like, oh, we can make this number higher, or we can drop the CG by this much if we lower the driver by this much, or do this. But at the end of the day, like we don't have like Lewis Hamilton driving our car. So if you might give up a little bit of like center of gravity height or mass for driver ergonomics, if your driver is able to comfortably drive the car over an endurance, it's going to end up being faster than something that looks better on paper.
Yep.
And that's something that's good to keep in mind in general, no matter what you're designing, not only with respect to tires.
I think the easiest way to get that point across would be to take it to the extreme. So we'll get into in a minute why you want to have the CG low, but most people here probably understand you want the weight on the car as low as possible. Well, what's the easiest way to get the weight low? Well, you could have the driver just lie down, right? But then they can't see jack shit. So how are they going to drive the car, right? So that's just taking it to an extreme, right? The car on paper would probably be very fast if the driver was just lying down. But obviously they can't drive the car without like some sort of periscope, which would make it very hard to drive.
Yeah.
Do you guys know how quickly a driver can turn the steering wheel?
How much do you go to the gym? That's really what it comes down to.
Yes and no. There's physical limits as well, but no, not off the top of my head. Maybe. I mean, actually, rack ratio is going to play a big part in that.
Yeah.
So it's real. Yeah, it's wheel angle, right?
Yeah. So rack ratio is going to be a big factor there.
So like, I think tying that together with like the dynamics of the car in terms of like how quickly the car responds will definitely kind of help understand like what's drivable and what's not.
Thanks.
In terms of like, can the driver respond if this becomes unstable?
Yeah, exactly.
To correct emotion, yeah.
Yeah, to correct emotion, yeah.
That's a good idea. Any other questions?
I had another question.
Yeah, go ahead.
Sorry, it's not related to this, but it's back to my original question. So when you're oversteering, say if you see like some huge horse-powered Mustang going down a straight, they oversteer because they're too much on the throttle, but their rear slips out and their car rotates. So is it actually necessarily true that all the kinetic friction is longitudinal, or is there actually a lateral component to it?
Well, so you can still produce a slip angle when you're in kinetic friction. It's just going to be lower than the possible slip angle if you were in static friction. So you can produce a lateral force while you're sliding, you can produce a longitudinal force while you're sliding. It's just that the mu's will go down.
So, but if you're, so I guess your tires are still pointed straight. You have no steering.
Which tire?
on
Sorry,
the
front tires or rear
rear
tires?
tires.
Okay.
So if you imagine a car going straight and they just 100% throttle instantaneously, request all the power out of the engine, and then their car slips out on the rear. So they rotate from the rear and their front stays because they still have traction there.
The front stays, what do you mean by the front stays? Are they counter
I'm
steering?
just saying that
Because
the
counter
car
steering is
rotates.
going to affect this a lot.
So let's take steering out of the equation, right?
Okay.
So just the amount of grip on the tire. So it's rotating. It's
Mhm.
all kinetic friction, right? But if it was only longitudinal friction, wouldn't it continually push the car forward just at a slower rate?
Okay, so if
roll,
you,
right?
so you're saying that if they're driving straight down the straightaway, and they just mash the gas and they have infinite horsepower, so the rear end starts burnouting, right?
Yep.
They're now in what I would call an unstable situation, but in theory, they will keep going straight without needing to turn the wheel, assuming they have no slip angles to start with. They'll keep going straight. But if they have any, because I would call this an unstable situation, if they have any sort of slip angle on either the front or the rear, they will spin.
Yeah, not only slip angle, but any sort of
Or any
disturbance,
sort
I
of
would
side
say.
force, yeah. Any outside force acts upon them in some way. If the driver sticks his hand out of the car and puts some drag on the left side of the car, they'll spin.
Or you think about unequal torque being applied to each wheel, or hitting a bump or something.
Locked spool, yeah.
Right, because it's like driving on ice at that point.
Exactly.
Yes,
yeah.
Very much so, yes.
Yeah. And in actual world, in actual scenario, your car is never straight.
Exactly.
It's always
agreed.
at some angle.
Yeah, I'm saying in theory, and I do mean in theory, if you were dead straight, you had a lock differential, both tires were identical, right? So they produce identical forces, then yeah, you could theoretically go straight and continue going straight while doing a burnout without steering, but in reality, it's never going to happen. That's a good question.
Thanks.
Yep, no problem. Anybody else? I like these questions. We don't even have to go through the slides. We can just keep answering questions.
I have a small question. Is there no better middle ground between the blue and the red curve, or are those like standard tires? Or
well, so there's a major difference in construction between the blue and the red, which kind of helps explain why they're the shape they are. So a radial tire, I don't know. As a kid, we played with tires on the playground, and you end up like cutting yourself on these steel plies that were or steel belts that were in the tire. So if we look at a tire from above, a radial tire has usually steel wires running along the circumference, right? So that's called a radial tire. And a bias ply tire has plies running at some angle, both in one direction, and cross plies running in the other direction, right? So what happens is once you get to a certain, once your forces are coming in at a certain, because you're producing a lat F when you turn, right? So you're bending the contact patch, kind of like this. And once it gets too far out of line, it's no longer stiff. It can't take force anymore because you're deforming the belts, the steel. Whereas a bias ply, since it's got these plies running at angles, it may not be as good longitudinally. That's a different question in terms of producing acceleration or deceleration, but it is able to produce lateral forces much more stably as we increase slip angle, which we see here for the bias ply, if that makes any sense.
Yeah, that makes sense.
Cool.
Ross, I got a question if I'm not skipping in line.
Go for it, man.
Am I right that a bias ply is not available for passenger cars anymore? or very discouraged?
For the
That was
most
like an
part,
older design,
yes.
right?
So one thing I haven't really covered here is rolling resistance. And rolling resistance is usually much lower for a radial than it is for a bias ply. I'm going to say usually, again, not talking in absolutes. So if we care about gas mileage in any way, shape, or form, the radial's probably going to win. And we do care about gas mileage a little bit because we do have an endurance or efficiency points based on our gas use, but that does not overcome the speed difference that is available by running bias plies and making it easier for the driver to drive quickly. But yeah, you're right. For the most part, street tires, you can't really get bias plies anymore unless you find some really old tires.
And I guess radial is, okay, so you get maybe a little less grip, but they maybe last longer, but they wouldn't be good for the extremes of racing. That's kind of general.
There are racing series that run radials, and there's also drag racing radials. Like I said, in some cases you can produce more longitudinal force with radials. That's not always the case, but in some cases you can. So there are some drag cars that run radials. That's also true, but they only have to go straight, right?
Yeah. Okay, thanks.
Mm-hmm. Any questions in the chat we're missing? Because I can't see the chat, so.
No questions.
Okay,
no
cool.
questions. It was a comment, but no questions.
Okay, so to finish up this slide, we've talked about pure longitudinal slip ratio and pure turning slip angle, but you can do both at the same time. You just can't do them as hard as you would if you could do one at a time. And that's actually where a GG diagram comes from. So if we look in the bottom middle graph, you can't really read the legends, but basically this is a sweep of doing a combination of slip ratio and slip angle at the same time to maximize our forces. So we are able to produce a force forward and left, I don't know which way is left for you guys, forward and left at the same time, as well as say backward and right at the same time. But we can't do it as hard in say going right as if we were just turning right. And what that does is it produces a circle. And this is where a GG plot comes from our ability for the tires to produce forces as a function of slip angle and slip ratio before we start to go into kinetic friction and lose grip. And for our car and most cars, the actual GG diagram is going to have a flat at the bottom. And that flat will change as a function of speed. Because the car can't produce enough horsepower to always be doing a burnout no matter how fast you're going, right? So if you have a nice like BMW or something, you can probably do a burnout in second gear, but you can't do a burnout driving down the freeway. You don't have enough power. And what that means is you don't have enough power to produce a high enough slip ratio to maximize your forward acceleration, right? So the fastest race car would in theory have almost infinite horsepower. So you could always be at the limit of the tire because we're trying to produce as much force as possible to accelerate the vehicle as fast as possible. But that's obviously not possible in real life. Any questions before we move on? Okay. So I guess we talked about tires being complicated, and they are. And one of the reasons they're so complicated is because there's so many different, some of them little, some of them big things you can do to change their mu. And we call those sensitivities. So like, are they sensitive? So one really easy one is they're sensitive to surface, and that's the right graph here. So if we drive on snow, the mu is really low, right? So we can't really produce large forces before we start going into kinetic friction. If we drive on dry asphalt, we can produce very high forces before going into kinetic friction. Cobblestones are a bit of a complicated case because they're bumpy, so you're going to have a big problem there. But wet asphalt, right, also has a lower mu. And that gets more complicated because you can hydroplane, which is when water gets stuck under the tire and you float up on the water. But this is one example of some of the sensitivities of tires. There's other sensitivities. We'll move from right to left. So the middle two blue graphs are the sensitivity of the tire we used to run to temperature. So basically the way we look at this is slip angle, right? So if we're turning the tire, and this is at a constant normal load of 250 pounds. So we start here with the tire just floating along, and then we turn to the right, and we end up over here before the tire starts sliding, going into kinetic friction. And then we turn back to zero, and we end up over here, and we turn the other way, but we end up over here. And if we keep doing that, eventually we can end up over here. Well, what was different between the first time we did it and the second time we did it? The tire got hot. So if we look at the bottom graph, that is the temperature of the tire during those sweeps. And we can see that the tire goes from like 85 degrees to a peak temp of 150 degrees Fahrenheit. And that has changed the mu of the tire, right? It got hot, it got grippier and stickier and softer. So now it can dig into the asphalt better and produce more lateral force before it breaks into kinetic friction. And lastly, and this is the most important one that's going to be kind of the basis for vehicle dynamics, one of the bases for vehicle dynamics and suspension, is tire sensitivity to normal load. So if we put, so let's look at the yellow and the red lines here. So if we put 400 pounds of vertical load on the tire, this theoretical tire, we can turn it and produce a maximum of 400 pounds of lateral load out of the tire. But if we double that and put 800 pounds of normal load on the tire and we turn it, we can only get, let's say, 700 pounds of lateral load out of the tire. So it got less efficient, right? If it was 1-to-1, it would be 800 pounds. So what this means is anytime we increase the normal load on the tire, we can turn it and we do get more lateral load, but it's not proportional to our increase in normal load. And if you don't understand this, please ask a question right now to help me get the point across to you, because this is going to come up for the rest of the conversation. Okay, I'm going to say you all know what's going on. Oh, okay.
Yeah.
Too many casses.
Any questions? This is
So
really
there's a
important.
limit on the lateral load you can get.
Yeah, so this is the theoretical. If we go back to, let me go back a slide. So if we put 400 pounds of normal load, right, and the driver was perfect, and they were able to, let's stick with the blue tire. If they were able to stay right up here, we would produce 400 pounds of lateral force. But when we put 800 pounds of normal load, this graph gets taller. Sorry, this is normalized lat force. So if they put 800 pounds, let's say this isn't normalized lat force, this is just lat force. So this is 400. So if we put 800 pounds, it would go up here or whatever, but this is only 700. Whereas if it was linear, you would get 800, right? Because you put 800 down, you get 800 out, but that's not true. The mu does not, the mu actually goes down. So the efficiency of the tire goes down as you increase normal load.
The mu is not a constant.
The mu is not a constant for tires. That is a big problem, yes. It goes down with increasing normal load.
So you get to a point where you can press as hard as you want, but you can't get any more lateral force out of it.
That theoretically exists, yes, where you would say put 1,000,000 pounds on the tire, and the difference between 500,000 and 1,000,000 might not actually increase the normal load, or the lateral force capability. But I would argue that to get to that point, you would probably destroy the tire.
Yeah. Yeah, you would.
But yes, theoretically that would exist, yes. And I guess you might be able to get there with a ton of aero, but actually that brings up an interesting point. So if we go back to Newton's laws, right, we said, come on. We said we're trying to maximize our acceleration, right? So A equals F over M. So we talked about the tires producing F, right? And we just talked about load sensitivity. So if the car weighs 400 pounds and it has, if the car weighs 1,600 pounds and it has 4 of those tires, how much lateral force can we produce? Let me go back to this graph. So if the car weighs 1,600 pounds and it's evenly distributed, how much lateral force can we produce maximum, assuming it stays evenly distributed with this tire on the left graph?
Would that be 800?
So the car weighs 1,600 pounds. If we divide it by 4, how much is that per tire?
That's 400 per tire. And then if you have 2 turning tires, then that'd be 800, right?
Ooh, that's good. Okay, so we will get to why that is incorrect. But let me just say all 4 tires turn the car. So now how much is it?
1,600 then.
Yes, hey, that's correct. So if we increase the weight of the car to 3,200 pounds, how much lateral force could we produce?
Would that then become 3,200?
Well, so again, so if the car weighs 3,200 pounds, how much load do we have per tire? Assuming it's evenly distributed still.
That's 600, right?
I apologize. I can math, I swear. Wait, 1,600 times 2, 3,200.
Oh, 800.
No, it's 8. Yeah, okay. I was going to say, am I just really bad at math? Okay, so if we have 800, that's fine. If we have 800 pounds per tire, how much lateral force can we produce per tire? Let's just start there, right? Looking at this graph. I wrote it out before.
Per tire.
700 per tire. So what is that in terms of total?
I see.
Right, it's 2,800. So the amount of G's we can produce with the 1,600 pound car, we could produce 1,600 pounds of lateral force. That's 1 G, 1,600 over 1,600. With the 3,200 pound car, we could produce 2,800 over 3,200, which is, I don't know, 3/4 of a G. I'm just making up math. I can't do that in my head. Right, so our actual ability to accelerate the car went down as we increased the weight of the car. Right, so it's in our best interest to reduce the weight of the car as much as possible. But what if there was a way we could increase the normal load on the tire without increasing the weight of the car? Can anyone think of a way?
The wings.
Okay, downforce. Yeah, downforce. Yeah. So
Colin Chapman, maybe you've got to manage the air.
Aerodynamic surfaces can produce normal loads without making the car weigh anymore. So we don't have to worry about accelerating extra mass. So we can make the car, quote unquote, weigh 3,200 pounds without having to accelerate 3,200 pounds. So then we can, let's say the car still weighs 1,600 pounds, but we have 1,600 pounds of downforce. So now the car weighs 3,200 pounds. So we can produce, we said, 2,800 pounds of lateral force, right? But since the car only actually has a mass of 1,600 pounds, right? Then we have 2,800 over 1,600. And now we're over 1 G of acceleration. So we can go faster, right? Does this make sense to everybody, or did I lose anybody?
Makes sense. I got a question. I was thinking the same thing about the weight. You want to be as light as possible so you could have the most grip, but is there a point where if you could make the car super light, would that be a bad thing? Is there sort of a minimum on the tires to get you to full grip, or do you want to go as light as possible?
As far as I think is reasonable, you're not going to be able to make the car too light to have problems. You don't want it to be negatively light. Like don't have a weather balloon hanging off the chassis so it floats, because then you can't, if the tires aren't touching the ground, you can't produce forces, right? But as far as is reasonable, no, that's not possible really.
Think about your mu increasing as you reduce load on the tire, and you're not really looking to get a high number of force. You're looking to get a high acceleration. So as long as your force to mass ratio is going
because we, like, as we increase the load on the tires, they do produce more lateral force, right? But it's just less efficient, and that efficiency, if you will, is mu. So as we decrease the load on the tires, the mu goes up. And if we're decreasing the load on the tires, the car is probably getting lighter. So what that means is we can produce higher accelerations because even though the forces are lower, the masses are even lower because our mu went up.
I got like a follow-up. So I was just talking with Qasim, basically asking, how do you know the ratios where the tire starts to lose its efficiency? Is that, and he was saying that the manufacturer will give you a chart. Is that something you figure out on your own, or is that like you just go off their numbers, or what do you do?
Well, so we pay for numbers, basically. There's a group of colleges, and we all pay money into what's called TTC, Tire Test Consortium. And they go and they take tires and they put them on sandpaper, like a sandpaper treadmill, and they push down on them and then turn them, or they try to accelerate them on the treadmill or decelerate them on the treadmill, and they measure the forces. And that's how we produce these graphs. And then what we need to do is ask ourselves, well, what's the mu difference between sandpaper and asphalt? And that's a different question. But the graph shape stays roughly the same. So we can scale the whole graph to different surfaces, as long as they're not too different. Like snow in this instance has very different shape of curve, right? But we assume asphalt and sandpaper have a fairly similar shape of curve. So the optimal slip angle, if you will, stays the same. It's just that the lat force goes down because asphalt has a lower mu than sandpaper. I hope that answers your question.
Yeah, that's really that's awesome. I didn't know that was available.
It's not cheap.
Yeah, wow.
It's not cheap and it's not perfect, but it's better than
definitely
nothing.
not perfect.
I have another follow-up. Is that okay?
Yeah, dude.
Yeah, dude.
Keep going.
Questions for days. Let's go.
Okay. So let's say you're at this example of like 400 pounds per tire, and then you got a downforce kit, that you designed. How do you know how far to go? Like, how do you know how
That's a
much
great
you want to
question.
add? Okay.
Okay, so we said downforce produces extra normal load, right? Which allows us to, in turn, produce extra lateral force, right?
Okay.
But what else does aerodynamics produce? It produces drag, and drag slows the car down.
Yeah.
So at some point in theory, you could have so much downforce that the car won't even go above like 30 miles an hour. And that's going to make you so slow that you're going to be slower accelerating forward. Then you will decrease your times by being able to corner faster, right? At some point, you're better off being able to go faster forward and corner slower. It depends on the shape of the track, right? So if the track is a circle and you're just going around in circles, right? Then higher downforce is probably better. If you're trying to go in a straight line only, lower downforce is probably better. And I say probably on purpose there, because you do need to be able to, you might be beneficial to have a little bit of downforce to increase your ability to accelerate the car by increasing the longitudinal force. But at some point, the drag is going to kill you, right? Because drag increases with the cube or square of speed, right? So the faster you go, the worse it gets. We happen to go very slow in the general scheme of things. So having lots of downforce for us is not really a problem. But we also can't produce huge amounts of normal load from downforce because we go slow as well.
I think I understand your connection that every team goes back to the tires because it kind of answers questions for them. Is that right?
Yeah. I mean, at the end of the day, we end up back where we started, which is how do we produce forces? Well, tires. That's the only way we can produce forces for the most part. The drag is a force, right? And that's produced by air. But the major forces on the car are produced by tires.
Very cool. Thank you.
Mm-hmm. Any other questions? Okay, so just to clarify, everybody understands that if you increase normal load on the tire, it gets less efficient So you still produce lateral force. It's just less efficient at producing lateral force because that's going to come up a lot.
Yeah. And also, for a given lateral force, the more you increase your slip angle, or for a given normal load, the more you increase your slip angle or slip ratio, your force will increase up to a point until you switch friction modes.
Are there chats? I'm seeing like pings.
Yeah, I got it open.
Okay, what does it say?
Brandon was saying he understands.
Okay, cool.
Nathaniel says diminishing returns, which is exactly true. That's what it is.
That's exactly what it is. It's diminishing returns. It's true for downforce as well. Who was it? Mark? Was it Mark that was saying? Yeah, Mark was saying something about, could we put too much normal load where like we don't get an increase in lateral force anymore? That's potentially true with downforce, right? If you kept increasing downforce, at some point, like you're going to go from 800 pounds to 1,000 pounds to 1,600 pounds to whatever, and eventually the increase in drag is going to be way more. It's going to be way more detrimental than the minor increase in lateral force or longitudinal force that you can produce, right? So there is diminishing returns with aerodynamics because of the tires as well. And another thing that was brought up, I don't know if it was brought up on purpose, but so because of these sensitivities, the track becomes a big driver of a lot of this stuff, right? We talked about aerodynamic causing drag. So on some tracks, you might want more downforce, like Monaco for Formula One has a lot of turns, right? So you might want more downforce. But Monza is mostly straights, so you probably want lower downforce because you can make up that time in the straights. There's also a temperature sensitivity, right? So if the track, and this applies hugely to Formula SAE, we have 3 events where the tires are cold and 1 event where the tires can get hot. So the 3 cold events are acceleration, skid pad, which is like 2 circles, and then you go over and do 2 circles the other way. And autocross, which is like a tight course, but you only do it for 50 seconds and then you stop. So for that one, the tires can get hot about halfway through. And then endurance is 30 laps of autocross. So we also have to balance a tire that produces a higher lateral force than another tire when it's cold, but that the worst tire when it's cold might be the better tire when it's hot. And we're not allowed to switch tires at competition. Well, we can switch tires, but we have to stay with the same compound and the same brand of tire. So while we might want to run a really sticky tire that operates at low temperatures on the first day, we have to run the same tire the second day. And that might overheat in endurance possibly if we ran a really sticky tire. So we have to kind of balance that. And we have ways around that as well. But yeah, any questions?
Yeah, Aaron's asking for us to talk about the reasons why there's diminishing returns as far as normal load to lat force or to mu.
So as far as the physics?
Yeah, he's asking why. And one is because rubber is kind of weird. And its properties change as you squish it.
So I guess the way I think about that is if I go back to this, right, and I didn't really talk about these pictures much. So let's take a closer look at the bottom right picture. So there's at least 2 major ways tires produce elastomers. A rubber is an elastomer. Produce forces against surfaces. Adhesion, which I don't really want to go into because it's intermolecular forces, and deformation. So let's think about deformation. Hysteresis is basically if I squish something and I let go, does it come all the way back? And how long does it take to come all the way back? That's hysteresis. But let's just talk about deformation. So if I have a block of solid rubber, and let's imagine that asphalt is really pointy. So if I put that block of rubber on a pin, right, it will start to deform around the pin, right? And because it deformed around the pin, I can put lateral force on it and it'll produce a force back because it's trying to, the pin's like digging in, right? If I double the force on the pin, on the rubber, and it sticks a little further in, the pin sticks a little further into the rubber, can I double my force? I mean, when it first started sticking in, I could get a lot of force, right? Because it was like, it started to deform the rubber. If I double the force, it's going to deform the rubber a little more, right? But not enough that I can double my lateral force before it skips off the surface. That's kind of what's going on. So a little bit of force will cause it to deform, and that allows you to produce side forces. But a lot of force will also cause it to deform more, but it won't allow you to increase your side forces proportionally. That's kind of what's going on if I want to simplify. Does that kind of make sense? I can't.
They say understood.
Okay, cool. We are done with tires. And we've kind of gone through all the questions. So tire modeling and tires are complicated, and I don't know everything about them. The only guy that probably does is Paseshka. TU Delft makes their own tires, so they're probably the best people to ask. Tires produce almost all of the forces with which we drive the car, longitudinally and laterally. Tires produce forces by distorting the rubber at the contact patch, and we simplify those distortions into usable numbers by talking about slip angle and slip ratio. Slip angle being turning the tire with respect to the rubber and the contact patch in the road, and slip ratio with respect to trying to torque the tire forward or backward with respect to the contact patch and the rubber. And normally those things will be in static friction. We talked about static friction force being higher than kinetic friction force in terms of doing a burnout versus like accelerating smoothly. And then tire friction is very sensitive to outside variables, or variables, some of which we have control over, right? So again, I will harp on this again. Normal load sensitivity is very important. Temperature sensitivity, we talked about with different events, can be very important. Surface sensitivity, if it rains, or the surface at Lincoln is scored concrete, which has a different mu than the surface at Michigan, which is asphalt, right? Tire age and heat cycles. So what this means is when you get the tire fresh out the box, right, you could smell it, right? And it smells like chemicals, right? And some of those chemicals are keeping the rubber soft. So as the tire gets older, those chemicals will escape, and the tire, if we think about it in terms of like, if you have a pencil, right? And you reach in your book bag and you find a pencil at the bottom of your book bag, and the rubber is like, the eraser is like hard as a rock, right? That's also an elastomer. And all of the chemicals that were keeping it soft are gone. Now it's just hard and you can't get any friction out of it. And the same thing happens to tires and heat cycles as well. So if I go out and I drive on a tire and it heats up, the heat will cause some of those chemicals to escape. And then the rubber will be harder the next time it cools down. Pressure sensitivity. So this has more to do with how the contact patch is shaped, usually, than actually the way the rubber is touching the road. But if we overinflate a tire, right, it will bow like this, right? So then when we touch the road, we will have a smaller contact patch than if we had the tire correct, right? And it would compress and we have a bigger contact patch. If we underinflate the tire, it'll actually bow like this. And again, we will have a smaller contact patch and also very flexible sidewalls. Camber sensitivity. So this is where if you've seen like a stance car, right? Like hella flush, right? The tire is tilted over. That does the same thing. So now there's only a corner of the tire touching the ground, right? So in theory, we would want very low camber values to produce high lateral forces. Sometimes that doesn't work out in practice, but we may or may not get there. Any other questions before we move on from tires? Okay. No doodles.
No doodles. All right.
So we skipped, this is vehicle dynamics.
Welcome.
It's mostly about keeping loads as evenly distributed as possible.
Yeah. This will be the very fundamentals of vehicle dynamics. And we're going to try and explain it in a way where even if you're a freshman, you can gain some intuition about it. So first of all, I just want to talk about modeling a little bit because we do a lot of it in vehicle dynamics, but this stuff here is applicable to anybody on the team if you're doing an FEA on your brake rotors or you're doing a CFD sim on your wings. All this stuff really applies. So whenever we model something, we're making an abstraction of reality. So it's not a one-to-one of what's really going on in reality. And we generally make simplifications when we want to model something. And it's important for us to know what simplifications we're making and how that might affect the results of our model and what we're seeing. So when you go about modeling, whether it's an FEA or CFD or some of the stuff we do here in VD, you want to think about what you want to model. So that will tell you what you're trying to get out of it. And with that in mind, you only want to make your model as complex as it needs to be. You don't want to make it arbitrarily complex to where you're either adding computation time or adding in factors that don't really matter. And the more complex you make it, the more room you add for you to make mistakes in your model. So you only want to keep it as complex as it has to be. And with that said, you need to really make sure you understand the fundamentals of whatever you're doing. So in our case, the fundamentals of how a tire works, how physics works, F equals ma, torque equals inertia times angular acceleration. If you're doing an FEA, that means you need to be able to draw the free body diagram of your FEA by hand and be able to know exactly where your loads are going or how your loads are applied before you go out to do a simulation. Because if you don't understand the fundamentals, you're not really going to be able to tell if what your simulation is giving you makes sense or is really usable. You're kind of just trusting a computer, and computers are dumb. They're just going to do whatever you tell it to do. They have no concept of whether it's right or wrong. So if you put garbage into a simulation, you're going to get garbage out. And it's really important to be able to distinguish between the two. So we talked about a little bit about like FEA on stuff or CFD if you're an aero guy. So what types of stuff do you guys think we would want to model in vehicle dynamics? Open to anybody if you have a guess. What does vehicle dynamics mean to you guys?
Dampers.
Dampers, sure. Nobody said tires, which is surprising.
We can also go back a slide. This is a very dynamic situation, right? What do you think is going on here? Right? How would we model this, and how would it affect the grip on the car, right?
Load transfer, maybe?
Yeah, that's a very good one.
Good one, yeah. You would also want to model your aero loads, right? Maybe not in the same way that you would do it for the aero guys doing CFD, but your aero loads go into everything. Like you saw, that affects the amount of force your tires make. You need to have some model of a powertrain, a braking system, as far as what forces and torques it can generate. So you kind of do a little bit of everything because we're concerned about the vehicle as a whole and making sure we can maximize our accelerations and points at any time so we can win.
And one other thing I would add to this is it's very important to not just make sure you understand the fundamentals, draw out free body diagrams, but how do you know if you're getting garbage, right? So it's very important, if possible, if at all possible, to go back and look at data or to collect data if you don't have it, to validate whether your simulation is producing garbage or if it's producing values that are what you expect.
Yeah, that's a great point.
Because oftentimes you will not know if it's garbage or not, unless it's ridiculous, right? Like, oh, our car can go infinitely fast. Yeah, my model's probably garbage, right? But, oh, we can produce 2 Gs of acceleration? Maybe. But we should probably go collect some data and see if that's true.
Yeah, that's a really good point. Cool. I don't know if I have anything else to say on that one.
Okay.
Ross, you want to take it away?
So Cass, you brought up an interesting point, something called load transfer or weight transfer, depending on who you talk to. A lot of people don't like it when you say weight transfer, but I like to say weight transfer, as long as we understand that weight is not the same thing as mass. So when we first start to look at the car, we oftentimes try to simplify, or anything really, we try to simplify it, right? So in the VD sense, we often simplify things by thinking about them in terms of point masses. So if we think about the car, we can say the car weighs let's stick with 1,600 pounds. And we can say that all of that, it's equivalent to having all of that mass at one point, as long as that point in space has the same distribution front to back or side to side as if we had the whole car. So if we chop the car up into pieces and we looked at where each of the masses were, we could put them in one spot. That would be the same thing for the most part, not in terms of inertia. That's a different problem. But for most simulations, we can think of the center of gravity having a certain weight or mass at that position would be equivalent to the whole car. So then we can start to use that concept to understand what's going on. So if you're just driving down the road, if you're on the freeway, you're 60 miles an hour, right? And you hit the brakes. What happens to your body? Someone can tell me. This is the easiest answer you're ever going to get. So nobody.
Lean forward.
Yeah, it put you get thrown forward, right? So what happens to the car?
Damn.
Yep, so the car also gets thrown forward. But let's examine why that happens and what that causes in the right picture. So the center of gravity is this black and white pie thing. That's the common picture or symbol for center of gravity. So when we hit the brakes, we're asking the tires to produce some force pointing backwards, right? To slow the vehicle down. The center of gravity is above the ground on this vehicle and almost any vehicle you're ever going to come in contact with, besides like a sailboat. So if the car weighs 1,600 pounds and the CG is 1 foot off the ground, right? Then if we're pulling 1 G of braking, we can produce 1,600 foot-pounds of torque, right? Because it's 1 foot off the ground and there's 1,600 pounds moving forward, right? You agree? Everybody agree with this?
Does everybody understand torque? Like how torque works? I don't know if we have freshmen in here that may not have gotten that far yet.
Hopefully, if we do have some freshmen that don't understand this, they will speak up because it's important.
I have no idea how torque works.
Oh,
yeah, me
thank
neither.
you, John.
Can you explain?
I could tell by your tune, John.
All right, Arash, you can explain torque.
Okay, so I guess the simplest way to think about torque intuitively is imagine if you had a bolt that was tightened down on something and you wanted to remove that bolt. If you went and you just grabbed it with your fingers and you try to unscrew it, it would probably be pretty hard, right? But if you went and you're smart and you grabbed a wrench and you put a wrench on it, all of a sudden it's a lot easier to loosen that bolt. So if you think about it, you have a point here and now you have your wrench handle and now you're putting a force this way, right? So that force in this lever arm here is going to create a torque here. So it's going to amplify the effects of your force on that point. And another way to think about it is if you're going to open a door, there's a reason why a doorknob or a door handle is on the opposite side of the door from the hinges, because that force you apply on the opposite side of the hinges makes it a lot easier to open the door. So if imagine you can get up and try this right now. It's a lot easier to open and close the door pushing from the doorknob than it is pushing from right where the hinges are on the door. So it's basically some sort of lever arm amplifying the effects of your force and a rotation that it causes.
Thank you. So I will actually start over on this a little bit. I'm going to alter this and make this 800 pounds because I forgot I have all the weights on the car already. So we have evenly distributed 400 pounds front, 400 pounds back. And we have 800-pound car now. The car just got a lot lighter for some reason, magic. And it's 1 foot off the ground, and we're pulling 1 G of braking. So we hit the brakes, and we asked the tires to produce 400 pounds apiece, right? And what that did was it effectively, we can slow the car down, right? But now the car is producing 800 pounds of forward force with respect to the tires at 1 foot. So we have 800 foot-pounds, and I hope we're all still following. We have 800 foot-pounds of torque, right? But that has to be counterbalanced by something, because some of the moments and some of the forces has to equal 0. So what ends up happening is we get weight or load transfer such that those torques are equal to 0. So this isn't going to work perfectly, but so we had 1 foot. I'm going to go down to the bottom picture. So we have 800-pound car, 1 foot off the ground. So we have 800 foot-pounds. So if this front wheel is 1 foot from the center of gravity, then we need to push up with 800 pounds to counterbalance that, right? So because then we have one moment going this way and one moment going this way, and they're equal and opposite, and they make 0. Yeah. I mean, I did that wrong, but that's okay. So let's say we're 2 feet away from the center of gravity now instead of 1 foot, right? Then we only have to push up with 400 pounds, because 400 times 2 is 800, right? We all following? So what ends up happening is you effectively end up moving that weight off of the back of the car to the front of the car to produce that counteracting force. So before, if the car was 400, 400, depending on the geometry of the car, and for this model, we just assumed it was all transferred, we needed 400 pounds extra to produce enough force to keep the car from basically flipping over, right? We had to come up with a counterbalancing force, and that force ends up coming from the ground through the front tires, in this case, when we hit the brakes. If we hit the gas, it would come from the back tires, right? Because we can't have, the back tires can't pull the car down, right? Because we don't have any, we're not bolted to the ground. So the front tires end up producing that force. And what that's called is weight transfer or load transfer. But let me make this, let's take this one step further and think about it in terms of our ability to produce forces. So if we went way back in our heads to like 5 slides ago, we said that, let's take a look back at this top picture. I'm going to erase all of our drawings. So we have 400 pounds on the front tire and 400 pounds on the back tire. Let's assume it's a motorcycle. How much longitudinal, so braking force, can we produce before we lock the tires? Let's go back and check. And let's imagine that this left graph is longitudinal force, not lateral force. So this is longitudinal force. Forget about that. So if we have 400 pounds of load on the tire, we can produce 400 pounds of thrust in any direction. So if we go forward again, we have 400 and 400. How much longitudinal force can we produce? Anybody? Bueller. Bueller. Bueller? Nobody?
Somebody knows.
Sorry, what? Somebody said something.
400?
So 400 per tire or 400 total?
Per tire.
So I agree with you, 400 per tire. So we said, forget that this looks like a Volvo, it's a motorcycle. So we have 2 tires. So we can produce 400 pounds of thrust this way with this tire and 400 pounds of thrust this way with this tire. So we can produce 800 pounds of force. Agreed? So now let's go look at the second state, the bottom car or motorcycle. If we have 800 pounds in the front and 0 pounds in the back, I'm sure you can tell me how much force the back tire, how much force can the back tire make? Considering it's not touching the ground.
0.
0, thank you. 0 pounds. Okay, so the front is at 800 pounds. So let's go back and look at the chart. So at 800 pounds, we can produce 700 pounds of longitudinal force. So what happened? We could produce, crap, let me annotate. So here we had 800 pounds of that way. Now we only have 700 pounds of that way. What happened? Well, we transferred load, and that means that we increase the load on one tire, decrease it off the other, and what ends up happening is we lost some ability to produce force because we're not evenly distributed anymore. So can anybody think of some ways we can make it so that there's either less load transfer or increase our ability to produce force or acceleration?
Would anti-dive?
That's a reasonably good question. So this gets kind of into suspension, but so the A-arms are like this, right? Normally they're parallel, assuming we're running a parallel setup, they're parallel to the ground. So we have a spring in here. I don't know if you guys can see the spring. And there's a damper inside of it, but let's disregard. This is not in time. This is a static model. So if we run anti-dive, that makes this face the CG. The forces are all still the same. What changes is the way that things react in time, potentially. But since this particular model is not talking about time, the answer to your question is no. That would not change the forces. That's a good one, though. Anybody else have any ideas on how we can reduce load transfer or alter load transfer?
Back.
Say again?
Move the CG back.
That's excellent. Okay, so what happens if we move the CG back to here? Well, I'm just going to do this real quick. But so now this first car, let's say, is 200 and 600, right? And then after we brake, now it's 400 and 400. Well, now Mark Lynn's car can decelerate as faster than the previous car. Would you all agree with me? Because it's 400, 400 versus 800, 0. Somebody give me a yes, that you're awake.
Yes.
Okay, cool. Okay, I agree with you, Mark. That's a good way of doing it. Are there any other ideas on how we can have this accomplished?
Could you put downforce in the back with arrow or something?
Yes, that could work. Would you want downforce just in the back?
Well, in the scenario where you're braking, I'd imagine you'd focus on the back.
Well, so at the end of the day, we're trying to increase our ability to produce forces that slow the car, so that act this way. Does it matter if they come from the back tire or the front tire? We're just trying to maximize the amount of force, period. So downforce in the back versus the front, if we're disregarding drag moment, it would be slightly more efficient to produce in the back. I agree with you, because if this is at 800 and we add 200 pounds of force, right, we get more mu than if we have 1,000 and 0. Would you agree on that? So in that respect, yes, you're 100% correct. You're better off having downforce in the back than in the front if you're just braking. I agree with you.
So Mark kind of got it a little bit, but
who?
What causes load transfer, right?
Yeah. So if we go back to my beginning, we have 800 pounds of load. 1 foot off the ground, that produces 800 foot-pounds of torque. So load transfer is caused by that torque. How can we reduce that torque?
Lower the CG.
There it is. Yeah. So if this is 6 inches, then this becomes 400 pound-feet. Right? This is, at the end of the day, why it matters where the car's CG is. This is why race cars all try to have low CGs, to reduce this load transfer. And if we take it a next step further, in so reducing load transfer, they increase the efficiency of the tires, which allows them to increase the amount of force they produce, which allows them to increase their accelerations. And this is not true just in the longitudinal sense, braking and accelerating. This is also true in the lateral sense, which we can see in the bottom left picture. And I don't really want to draw the whole thing again, but the same thing happens when you turn the car. So you produce a lateral force at the tire, right? And that tries to roll the car over. And you feel this when you drive down the road, right? If you jink the wheel, you get thrown out the side window or towards the passenger, right? And so does the whole car. And that is weight transfer. So how can we reduce that? Mark's 100% correct. We can just lower the CG. We can lower the mass of the vehicle. That will also reduce the total amount of torque, right? We can add downforce to the side that is going to be reduced. And actually, if we take, I don't remember who it was that said we could move the CG back, but whoever said we could move the CG back. So think about, let me take this a step further in terms of interesting. Is there a race series that only turns one direction? Maybe in the chat.
Are you seriously thinking about NASCAR?
Yeah, I am thinking about NASCAR. So they only turn left. So is there any reason for them to have the CG in the middle of the car? Or would it be better if they had the CG on one side of the car so that after they turn, their load is evenly distributed? Interesting. There's a bunch of stuff in the chat, I think. Is there?
No, Alex also guessed lower CG correctly.
Okay.
Ross.
Yes.
What if I made the car shorter?
Ooh, that's very interesting. So let's talk about brake. Let's go back to the braking case because I've drawn all my drawings on the braking case. What if the front tire wasn't here and the front tire was over here, right? So we still have an 800-pound car and we're still 1 foot off the ground. So we have 800 foot-pounds of torque, right? But now, instead of being 2 feet to the front tire, which caused a shift of 400 pounds to produce enough torque, right? 400 times 2. What if this was 4 feet, right? So now we only have a shift of 200 pounds because 200 times 4 is 800. So we can make the car longer to reduce our longitudinal brake transfer. Or we can make the car wider to reduce our lateral load transfer. Does anybody see any problems with making the car wider or longer? Let's stick with wider. Does anybody see any problems with making the car wider? Let's take it to the extreme. What if you make it 10 feet wide? What happens?
Turning issues?
Well, will it even fit on the track?
Yep.
That becomes a problem, right? But let's also think in autocross, there's this thing called a slalom, which is just a bunch of cones that are lined up in a straight line. And you're required to go around them like this. So what happens if we make the car infinitely narrow, like a laser beam? What happens? Well, we can go straight through. We don't have to turn, which means we can go faster because we didn't have to slow the car down to turn. Infinitely narrow is not actually possible, but that's a different problem. But what happens if we make the car really wide? Well, now, if it even fits, we have to make these really big arcs to go through, right? Which slows us down. Even though our load transfer is low, we still have to slow down to make those corners. So we end up going slower through a slalom. But because our load transfer is lower, we may end up going faster around a circle. So if we're just doing circles, and there's an event that just does circles, it's skid pad. If we're just going around in a circle, we could be faster because we have less load transfer. So we have to balance between our ability to go around slaloms quickly, where we want a very narrow car, and our ability to go around in a circle very quickly, where we want a very wide car. And that's just one of the many trade-offs we have to make in designing the vehicle. Does this make sense?
Everything's a trade-off.
Yeah, almost everything in engineering, forget VD, everything in engineering is a trade-off, even if it's a cost trade-off. But does this make sense to everybody? If it doesn't, please ask a question. I am more than happy to reword or try to explain it a different way.
This is really like a key like application of tires being sensitive to how much load you put on them, and that diminishing returns we were talking about before, and how it can affect the overall accelerations you can produce.
Okay, then we'll continue on.
All right, let's do it. So we're gonna move into more of the dynamics a little bit, and kind of look at load transfer and tire loading in a more dynamic sense than we have. And Ross talked about a little bit on the last slide, but we mentioned static models and dynamic models. And a static model, you guys might think of maybe your CE 112 or statics classes, where you're just like, you have a beam that's like being loaded or a truss that's being loaded, and nothing's moving. And that's not necessarily what a static model is. So a static model could be anything, but you're looking at it in snapshots in time rather than continuously through time. And like I said, it's not limited to what you would normally think of when you think of as being static. So for example, you guys on the load transfer stuff, it was pretty intuitive for you guys to think that it's something that happens dynamically, right? You press on the brakes and then you get a torque and your body moves forward and everything. That's something that happens dynamically, but you can model it statically. So on this graph right here, this is a graph of your total lateral load transfer as a function of acceleration. And you can actually just look at it at each point in time, and you kind of ignore the dynamic side of it. So in this case, for a static model, or actually for a static model in general, the same input will always give you the same output. So for this specific car I modeled this on, the same acceleration input is always going to give you the same amount of load transfer for this specific car. Or if you think you had some sort of black box or function that every time you put in 2, it gave you 10, that would be a static model. And they're generally viewed of as steady state. So when you're transferring load, this isn't worried, a static model isn't worried about like how much time it takes the load to transfer or how the load transfer happens. It's just at the end of the load transfer, how much load has been transferred and how much load is on everything. And that could be more than enough. A static model can be more than enough for a lot of situations. Actually, in vehicle dynamics, even though we're called dynamics, we use static models like all the time. And a lot of dynamic situations you can break up by taking a lot of really tiny snapshots in time and doing kind of like quasi steady state or quasi static or quasi transient models, because it's kind of hard to model things dynamically sometimes. So a dynamic model, based on everything we just said, is not static. So now you're worried about how things move as a function of time or move through time. So now if we're thinking about our load transfer case, we're worried about how much load is being transferred for every moment in time, how the suspension is responding in like kind of real time due to that load transfer. And for a dynamic model, your input to output isn't always the same every time. So your input can depends on kind of what state you're in. So let's talk about, let's think of an engine torque curve, right? For you powertrain dudes. So here you have the torque your engine's producing, and here you have RPM, right? So it's gonna look something like that or something, and falls off, right?
I mean, if our powertrain guys are really, really good, it'll just be infinite all the time, right?
Yes, it just shoots up. There you go, John. JJ. So
below 1 mile an hour.
That's so based on what I just said, is this torque RPM graph a static model or dynamic model? Any guess? Why do you think dynamic? I should always ask and why every time I ask everything, because I'm always going to ask why after anyway.
Because even if you're right or wrong, your reasoning may be correct or incorrect, which is more important. Your reasoning is more important than anything else.
I mean, asking why is probably the most important thing.
Whoever it was that said dynamic, I didn't see who it was. Can you explain why? Why do you think it's dynamic?
Okay, I appreciate the answer. So Alex says static, and he's exactly true. So this doesn't worry about the engine changing in time, right? This is just it's a mapping of RPM to torque. So every time I give this an RPM input, the engine has this amount of torque. So it's a static model. So if we want to think of a dynamic model of an engine, we would be trying to look at something like throttle response. This plot doesn't tell you anything about throttle response, right? It just tells you for any engine speed, what's your RPM. So if I'm down here, this might be something that's kind of intuitive to you guys who have driven cars before. Your throttle response isn't the same when you're at low RPM as it is when you're at higher RPM, right? And that's what I kind of mean by the output depends on the state. So your engine isn't going to respond the same to a throttle input for a low RPM as it would for a high RPM. And this static model doesn't take into account that it takes time for the engine to react to an input because the engine has rotational inertia. There's friction you have to overcome. There is things like the size of your plenum that will affect how quickly the cylinder fills, or which affects your throttle response. So that's kind of a good way of thinking about the different things you can look at with a dynamic model versus a static model, because now you can look at those time transient responses of a system like throttle response. Or for our case, we talked a lot about normal load, right? And how normal load can affect, the normal load on the tire can affect how much grip it can give you. And if it varies, the normal load varies, that affects how much grip it can give you. So on this example down here,
at the bottom right.
Bottom right, yeah. Sorry, I was drawing. I realized it doesn't pop up as I'm drawing. So on the bottom right here, this is a dynamic model of the car suspension. So this input, if you think this axis, sorry, I should label the axis, but this is inches, and this is time on the bottom. So the input here is the surface of the ground. So over time, the ground's level, and then it dips down to about 1.25 inches, and then it stays there for a little bit and it goes up. So you can kind of think of this as the car driving through a pothole, right? So in the other two plots, the purple plot is the response of the sprung mass. And if you guys aren't familiar with the term sprung mass means everything on the car that's supported by the springs, the suspension springs. So the chassis, the engine, in our case, the wings, you, if you're in the car, your cell phone that you're using to look at Instagram while you're driving and you shouldn't be, that's all considered sprung mass. And unsprung mass is the things that aren't supported by the suspension springs, like the tires, the wheels, the brakes, all the stuff that's kind of, if you think of it like underneath, in quotes, the suspension, that's the things that are unsprung mass. So as we drive over this pothole now with a dynamic model, we can look at the change in position of our sprung mass and unsprung mass. And what do you guys think is happening to the load on the tire as it moves like this.
It's varying.
Yeah, the load's changing, which means your grip's changing, which means as you go over a bump, your tire is going to oscillate. It's going to move around, which means it's going to move up and down, right? So your grip's going to change as a function of time, which you wouldn't be able to capture thinking about things in a static model. In a static model, you would probably only get this, and then like if it was flat down here, you would get this, and then this very end section. You would lose all that variation in normal load. I mean, you guys are quiet. It's not as fun.
I know.
I feel like I'm talking to myself. Ask questions, man. I'm not sitting here like just talking for my own benefit. Me and Ross are trying to teach you guys. So if you guys have questions and answers, yeah, go ahead.
Go ahead, Cass.
I have a question. So yeah. So this sort of links the sprung and unsprung mass that you were mentioning to what Ross was saying before regarding load transfer.
Yes.
So thinking on a suspension point, right, or like on a suspension perspective, and having now that you mentioned, like obviously unsprung mass is like the tires since they're on the road. So does your suspension assist with that load transfer scenario? Like I'm assuming you can probably like adjust from that perspective. So how do you
Good question.
like do you adjust the rears separately based on your CG, and so like how do you go about all of that?
What you're asking is very complicated.
Yeah, it gets more complicated.
I will give you as simple of an answer as I can.
Yeah, please.
And then I want to address something that somebody else said earlier, something that somebody else said way back that I can now have a better answer. So, or I can now give a better answer since we've talked about dynamics. So let's look back at the braking case. Somebody said something about anti-dive. I don't remember who it was.
I think it was Aaron.
So we're going to talk in a minute about dampers, but dampers allow us to control forces in terms of speed, and speed has a time component. So we're allowed to control forces in terms of time and load transfer in terms of time. So if we have forget parallel A-arms. If our A-arms are perpendicular to a line towards the CG, right, then they have no stiffness with respect to the CG trying to fall forward, right? Because the CG, we said the CG was trying to fall forward and it was rotating about the ground, right? So the CG is trying to fall this way. The A-arms have no stiffness with respect to the CG. So now if we have a spring in here, right, that spring is going to take all the load that it takes to push that CG back to where it belongs, right? Or counterbalance its force. So if we put a damper in there, we can control how fast it is allowed to move forward, because a damper produces force as a function of speed or time input, right? And that's kind of, and so anti-dive is the opposite. So anti-dive can be a good or bad thing, but anti-dive is when the A-arms are facing towards the mass. So then all of the load is going into the A-arms and skipping the springs and dampers. And what that means is the load is transferred instantaneously. So you would go from 400, 400 to 800, 0, almost instantly, because we assume the A-arms are infinitely rigid, which they're close, they're pretty rigid. And what that means is you would basically you would go from 400, 800 on the front tire in terms of normal load, right? And what would actually happen is you would compress the tire and it would bounce a little bit, because the tire is a spring, right? It's rubber and it's got sidewalls that flex. And this would cause an unwanted thing called, that we know, right, normal load variation. So if it's bouncing up and down, then we're getting these changes in possible grip, which makes it very hard for the driver to be right at the limit, because the limit is moving, right, as they're trying to brake. But this may be advantageous if we want to limit our movement, right? So a damper and a spring, requires displacement in order to produce a force, right? K times displacement is force.
Damn it, Ross.
I'm sorry, we'll get to it. I didn't want to go too fast. But what happens if our front wing is hitting the ground when we hit the brakes? Maybe we want to put in a little anti-dive, because then the load, instead of going into the spring and causing the front to smack the ground, will go through the A-arms. And then that will mean that the spring compresses less. So the front wing won't smack the ground and explode. Because I know how much the aero team likes building new front wings.
Got it.
I hope all of that makes sense. And that's super simple.
Very.
And we'll get more complicated in a minute. But the other thing that I wanted to mention was we talked, Arash, you had a good graph of lateral, let's call this longitudinal acceleration, the left graph.
Yeah.
Let's call this longitudinal acceleration, so braking or accelerating, as a function of weight transfer. So somebody said something about adding a wing to the back of the car to increase the rear load on the rear, right? So I said, okay, so then let's say this is 800 and this is 200, right? But we've just made our system a little bit more complicated, because now our load distribution is a function of vehicle speed, because the faster the car goes, the more downforce you can produce. So now, when you hit the brakes going 60, you might have 200 pounds of load in the rear. But as you get down to like 10 miles an hour, you don't have any load in the rear, right? So now you might be locking the rear tires. That might be a problem, especially if you want to keep going straight, right? So there's all these things that come into play that need to be thought about, or if we don't think about them, they can come back to bite us in the ass.
Wow. Thanks, guys.
Yeah. There's
This
also
brought up, like a million other questions.
No,
but this
yeah,
clears up, it clears up my initial, like the overview. Thank you.
Yeah, we all just realize how much we don't know. But there's also the case where having different spring stiffness front to rear can affect your load transfer in a lateral case. It gets like really complicated. Cass.
But you would define that based on your competition or whatever you're trying to go about, right? Your
Situation.
track.
Yeah. What you want depends on your situation, the track, like you said.
Yeah, so when we move on to the next slide, it'll become maybe a little more clear. And I don't know how many people in this conference room are mechanical engineers or have taken a class like vibrations or controls. But like this bottom right graph, right, we can change the shape of our sprung and unsprung mass response to this pothole by changing the spring rate and the damping rates. We can change the shape. So we can make it so that it doesn't overshoot very much, right? So we could make it so that potentially, or we can reduce the mass. Reducing the mass helps everything. So if we have no mass, it just follows the curve perfectly, but that's not possible. So we can change our damping and spring rates. So maybe it follows the curve better, right? Maybe it damps out faster, right? And it doesn't overshoot as much, because overshoot in this case means normal load variation, which is hard for the driver to control. But that may be advantageous for a pothole, but that might be super shitty for a speed bump, right? Or when we corner the car and it goes into roll, maybe that particular spring rate or that particular damping rate is very bad for a different sort of motion. And the damping, we have the ability to have two different damping ratios, sort of. But the spring rate is pretty much fixed. So in some ways we have to, again, as in engineering, we have to compromise. And in something, ideally, we would figure out what makes us the fastest on the track or in different events to maximize our points to win. It all comes back to that.
Cass.
Thank you. Yes.
I have a quick question for you.
Mm-hmm.
On this bottom right graph, do you care about unsprung mass or sprung mass response?
On the bottom right graph, which one do I care more about? Okay. I would assume that you would care more about, in this case, the unsprung mass, because that's your tires defining everything else. But at the same time, your sprung mass is what's shifting your CG slightly, throwing it all over the place. So, but if I had to choose, I think I'll go with the unsprung mass, which is closer to your input, which is better. Am I correct?
Sure, yeah. What if you're an aero guy?
If you're an aero guy, you definitely care about your sprung mass because that's shifting all your AOAs and all of that based on, you know, your aero package.
Exactly.
So,
okay, cool.
Yeah.
All right, Ross, let's go on.
Okay, sounds good.
Thank you.
Yeah.
Maybe. Oh, now we just skipped to the end. Okay. There we go.
So Ross already explained the slide a little bit, so I'm going to try and breeze through it a little bit quicker. But do you guys, almost everything on the car either literally is or can be modeled as a mass spring damper system. And just to go over it really quick for you guys who don't have who might not have taken a vibes class or dynamics class, just to kind of help you guys get some intuition. Let's say you had some mass hanging from the ceiling, right? And let's assume there's no air resistance, there's no like internal forces or anything. If you pulled on this mass down a little bit and let go, what would happen? Anybody?
These are the easy questions, man. You guys should be answering.
These are free.
These are free.
Boing boing. Aaron's right. It would be
boing boing. That is 100% the correct engineering jargon answer. Boing boing.
And how would it look if we had no air resistance, no internal forces? It would boing boing at the exact same amplitude forever, right?
It would never stop boing boing.
Yeah, it would just keep boing boinging. So
I have to use that the rest of the presentation.
The reason we have that boing boing is because, like Ross mentioned, springs produce a force based on their displacement, right? So if I pull the spring down this way, it's going to make a force this way, which is going to pull up the mass, and then the mass is going to compress the spring, so the spring's going to push it back down the other way, and that's just going to keep going on until everybody's dead and the universe dies. So that is what we would call an underdamped system, or an undamped system entirely, is one that goes on forever. So on our car, and I mean everything in real life has damping. In our car, our shocks are our dampers for this case. Just keep it simple. And like Ross mentioned before, dampers provide force based on velocity. So if you look at this equation for the damping coefficient, how do you get a force out of this? You multiply it by, in this case, inches per second. So you multiply it by a velocity to get a force. So that means dampers force also changes based on velocity. So if you think about the case of our car, if it's the driver like putting a steering input and the car's rolling, that interaction or that input is going to have a different velocity than you driving over a speed bump at 100 miles an hour or driving over a pothole, which is all going to give you different damping. Yeah.
If I may for a second. So I'm pretty sure most of us have driven down the freeway and seen a car with quote unquote blown shocks, right? So their dampers are not working particularly well. And if you see them driving down the freeway, they hit a bump and the car just goes, whoa, 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 whoa. That's because there's no force slowing that oscillation, which is what the dampers do.
Sometimes you can even see their rear tire just like doing this, or whatever tire has a blown shock, just like rapidly going up and down. So yeah, the damper provides a force. So let's say the spring's providing a force this way, the damper is going to provide an opposite force that kind of slows down that motion. You can think of it like friction. In some cases it's literally friction, in some other cases it's not, but you can think of it like a friction force that's slowing down the mass's motion and controlling it.
And I think the example we were using here was, if we go back to the example we used earlier to talk about torque, we talked about opening and closing a door at the door handle versus at the door hinge. So if you think about the doors at school, they have this thing at the top usually, and that's a damper. So if you open the door and you let go, it doesn't just smack back in your face. It slowly comes closed. And if you're an asshole like me and you open the door and you see someone behind you and you want to try and close it on them, you have to push really hard to close it, because the damper is fighting you the faster the door tries to close.
Yeah. So that's a pretty good intuition on a damper providing force based on velocity, like resistance force. So if we look at this bottom right graph now, you can see how the oscillations change as a function of how much damping you have, right? So damping, if you think about, in our case, when we're talking about a tire, every time you have this oscillation, your normal load's going up and down and up and down and changing, and your grip's changing. So damping is pretty important in being able to control that normal load variation. And I want to speed through this a little bit since we talked about it and we're running a little bit over. But one other important thing that's going to come up later on that last slide is how many degrees of freedom does this have? Which means in what ways is it allowed to move or rotate? And in this case, this can only go this way or this way. So it has 1 degree of freedom, and that's going to come up later. Just keep that in mind. Does everyone understand the basics of a mass spring damper?
If you need clarification, please speak up.
Yeah.
Again, this only gets more complicated.
Yes, it's going to get more complicated.
Okay.
Understand how it works and why those oscillations are important. Okay, so now we kind of have like the simplest model of the car that we can, which is 2 mass spring dampers connected to each other. So here we have, this is a quarter car model. So this is 1/4 of the car, 1/4 of the car's mass right here. So it's like, if you just took the left front corner, it's like 1/4 of that part of the engine, 1/4 of you, and now you only have 1/4 of your Instagram followers. So you have the 1/4 of the car, and then you have
the rest of them are really weighing you down.
we have 1 tire and wheel. So your unsprung mass here is your tire, your wheel, your brakes, all the weight of the unsprung mass on, let's say, the left front corner in this case. So this KS here is your suspension spring, and this is your suspension damper. And tires are actually air springs. So they actually have a spring rate, which might have been intuitive based on how we were explaining them so far. So the tire spring rate can change based on how much pressure you put in the tire. If you've ever seen a car driving down the road with a low tire, you physically notice that tire is a little more squished because it has less air in it, so it has less spring rate. It's not going to hold up the car's weight as well as a really pumped up tire. So pressure can affect the spring rate. Temperature, by the way of changing pressure, can affect it, and temperature can also change the properties of the rubber, which can affect spring rate, and so can normal load. So a tire has a spring, and it also has a damper here. And the tire's damping and spring rate are kind of sort of given. Like you can change them, like I said, with pressure, but you're never really going to adjust the tire pressure to adjust the tire spring rate. They're kind of what they are. And in this case, ZR, you can imagine like being some undulations in the road, like the pothole I showed you in the graph 2 slides ago. That was built from a quarter car model. So in this case, we can give some input to the wheel, and we can see how the unsprung mass and the sprung mass respond in time to that input. So why is this useful? Why do you guys think this would be useful? Why do we even want to bother modeling this?
And we kind of already covered it a little bit.
Isolation, what do you mean?
Like you said, each corner of the vehicle will respond differently, on like a different terrain or whatever. So you can maybe isolate how one side would react to a certain instance.
Exactly, yeah. So it gives you a very simplified view, not only to isolate one corner of the card, but to look at how different changes affect everything. So let's say your aero dude, Nathaniel, comes up to you and he's like, man, I got this really cool aero setup that is going to stall if the car pitches 0.1 degrees. So I want to run these really stiff springs. And I mean, you don't know what do stiff springs do on the car. So you can go to your quarter car model and you raise this. And now if your spring force is outrunning your damper force for this really big springs he wants, right? So if your damper can't really control it, now your normal load's going to be oscillating like that, right? So you can look at it to how different spring rates affect your normal load variation. And you can look at it if you're thinking about running stiffer springs for whatever reason, do you have enough damping in your shock to be able to damp that oscillation? And what damper setting would you even want to begin to think about using in that case?
And actually, that brings up a good point. In terms of Formula SAE versus Formula One, or when we think in terms of at the end of the day, we want to win, so we keep stepping back, right? So let's step back to, we want to have the maximum normal load on the tire at all times. So Formula One, usually aerodynamics takes precedence, and that's because they're going fast enough that even if their damping and spring rates end up fucked because they have to run really, really stiff springs, the increase in downforce that they can get by doing that means that overall they have more grip, even if the tire is bouncing all over the place. The grip on average is higher, as long as the driver can drive it, right? For us, because we go so slow, usually we can just tell the aero team to fuck off. We're not going to run really stiff springs because we need to make it as easy for our drivers to drive as possible, or we're going slow enough that the increase in normal load variation from the tire bouncing all over the place is not worth it for the minor increase in aerodynamic performance. But in some cases, like Formula One, it is.
Exactly. Yeah, so if you guys want to think about like how one corner of the car behaves over bumps,
you beat me to it.
Like visualize it. This is a good way to think about it because it's basically what it is. So now you have two masses that are connected with springs and dampers between them. Yeah. So talking about degrees of freedom, in this case this has 1 degree of freedom. This has 1 degree of freedom. So together they have 2 degrees of freedom, which means this can move up and down on its own, and this can move up and down on its own. So degrees of freedom just means how is my system allowed to move? Like what kind of movements can it do? And that's going to come into play on the next slide. Okay, I went kind of fast. I think everybody understood this in a mass spring damper.
Yeah, let me go ahead, Cass.
Sorry, I just had a quick question, but I can wait. Maybe you get out.
No, go ahead.
Okay, if you want to wait 1 minute. So if we go back to this being the road surface, if we have this speed bump here, right? We want to make sure that the tire is in contact with the road at all times, if possible, and we want to reduce normal load variation, right? So when it comes up this surface, we want to make sure that it doesn't go wee, right? We want to try and make sure that it goes, like this, and it might oscillate a little bit here, right? That's really the goal.
Yeah, and this lets you analyze how your spring rate and your damper settings can affect that oscillation.
For various
at least
inputs.
For
we
one
can test
corner
all
of your
sorts
car.
of inputs.
Yeah, you can have a Arnold Schwarzenegger step change. You can have a speed bump, pothole, whatever you want.
Curb.
You can have some guy going crazy doing a sinusoidal input. Yeah, you can really do whatever you want. Okay, is everyone on board? And all of these things, like I said, everything comes down to this basic equation. If you wanted to model this, you start with the sum of your forces equals mass times acceleration.
And if you are on...
Go ahead.
Go ahead.
No, I was just going to say you would just need one of these for each mass that you have.
Yeah. And if you are on board, I would suggest you get off so that the car weighs less so we can go fast.
That's pretty good.
Okay, cool.
Okay. So wait, I'm sorry. Before you move on from the quarter model, So my question is: are there constraints when you as in the quarter car model? Can you only, I guess, simulate it for certain like a straightaway or is there environments where this really is more applicable? Because I can see this being I mean, I guess when you go into like a slalom, then is the quarter model still like a viable option to look at, or
Yeah,
that
so
way? Yeah.
That's a
a
good question.
slalom would just change how this input looks. So this input, it doesn't have to be strictly the road like moving, right? This could be some like the driver turning, and now you have some load transfer, and that's going to compress or extend this system. Or if you're going through a slalom, you can think of a slalom as kind of like a sinusoidal input, right? If you think about one corner of the car as you go through a slalom, that corner is going to have load transferred to it, so it's going to compress. It's going to get unloaded, so it's going to extend. So if you put some sinusoidal motion into this, you can look at how this would respond to a slalom. And so you can see it based on like your spring rate and your mass and your damping. Sorry, dude, I don't want to keep cutting you off.
No, please go ahead.
My thought. So let's say you had your sinusoidal input, right? And your damping and everything is going to affect how well you one, you track this input, and two, when you suddenly change direction, how's that going to look?
And this quarter car model will not be able to model like things that might make it very difficult to drive through a slalom, like the normal load variation difference between front and rear, right? So like if the rear becomes light, then you might spin out in the slalom, right?
Yeah.
So this model is one wheel, and what we can do is we can take 4 of these along with a bunch of other equations and turn them into an entire car.
Okay, so I see. Okay, that's so, because I figured like what I was looking for is like, you want to really see not just how that one corner of the car acts, but how the vehicle acts throughout. Like how is the one side to the other side. So I guess you can eventually connect 2 of them or even 4 of them.
Yes, that's 100% correct, yes.
For a pure quarter car model, those are the types of things that you can look at and make use of it for, which is a lot of shit.
Yeah.
Yeah.
And you can do simpler versions of a slalom even with a quarter car model. They just won't be perfect, right? And they may not even be valid, but it comes back down to basically putting in a minimum amount of effort to get a reasonable result.
Yeah.
And in this case, a quarter car model is probably not good enough for what you're suggesting.
Yeah, it's not. You would, like you said, you want to do half a car, but I guess in your case it would be transversely half instead of longitudinally half.
Yep.
All right.
Thank you.
Yeah. Speaking of half car stuff.
Yeah. Wow. Funny you should ask, Cass.
Yeah. So now we have a half car model, except front to back. So you imagine you're riding a bicycle. You have one front tire, one rear tire. So now you get another quarter of your Instagram followers back, and we're adding a quarter to the car and adding 4 times the complexity into it. So the reason why I brought up degrees of freedom, because I think this is going to come up, is this system has 3 degrees of freedom. What does that mean? That means our bike can move forward and back. It can move from a driver's perspective. It can move left and right, and it can rotate about its CG. It can do this rotation.
Yeah. So what I would say is we actually took the quarter car model and we threw it away because that was moving vertically.
Yes.
So we are ignoring vertical movement here. We're assuming we're driving on like a piece of glass. It's like perfectly smooth. There's no bumps up and down.
Mm-hmm. And we're also, if you think about a bicycle can tip over. This cannot tip over. That's not one of its degrees of freedom. So it could just accelerate longitudinally, laterally, and yaw. So it can rotate about its CG or some other point.
Our CG in this model is at the ground. That's why we don't tip over.
Exactly. You imagine this is like one atom high car. That's what it is. So what a half car model does, where a quarter car model let us look at some like dynamics of suspension and dampers and everything. This lets us look at a very simplified view of the dynamics of the car, at least in acceleration. So just to clear up some terminology here, now since we have a front tire and a rear tire, we can steer the front tire. So we have this delta angle, which is the steering angle of the tire. And as you guys know, alpha, I'm not sure if Ross mentioned it,
no, I didn't.
Alpha in this case is your slip angle. So now you have steer angle, you have slip angle, you have some like rigid beam connecting the 2 axles, and then you have your CG, in this case, right in the middle.
And whoever it was earlier when we were talking about our lateral force capability, and I said we'll get to it, but all 4 tires steer the car and can produce lat F, this is getting to it.
Yes.
So pay attention.
This is definitely getting to it. So some things I want to point out and clear up. And this is where like a basic understanding of torques is really going to come into play. So one of the first things you guys notice is that the lateral force from the front tire is always perpendicular to the tire. It's not actually purely pointing straight into the corner. So now you have some force components that are this way, and now you have a force component that way of that. Do you guys agree? So what that means, sorry, what'd you say?
So no, we're on the same page.
Okay, cool.
Yeah.
So what that means is you have actually some force, some like drag force that's slowing you down, which means that in order to keep steady state, you need to have some input force or drive force from the rear tire to kind of balance that out.
You need to have some drive force from a tire.
Yeah, yeah. Shit, dude, my voice is going away. So another thing I want to think about. So a front slip angle seems pretty intuitive to generate, right? Because we kind of talked about it in the way where you have your, sorry, that was a terrible, those are worst
Awesome
rectangle.
tire.
I tried to draw
that's a
because I was trying to just draw the tires.
Well, so we talked about if you had a tire in your hands
Yeah.
and you smooshed it against the ground and you turned it, you would generate like a stretch in the tire, right? So
Yes.
that's what we're doing in the front. We're turning the tire and we get a free slip angle.
Yes. So your twisting or turning in this case comes from this delta, this steering angle. So you input a steering angle, and that's going to twist the tire, and it's going to give you a slip angle. And you know if you have a slip angle, you're going to have some force, right? So now let's imagine in our little bicycle or motorcycle, it's not really apparent immediately how this rear slip angle gets made, right? Because you're not steering the rear tires in this case. So how do you have a rear slip angle? So let's think of this like a motorcycle. And let's say you got Arnold Schwarzenegger on your motorcycle and he's riding through the aqueducts in Terminator 2. And he's trying to dodge one of the pillars in the aqueducts, right? So at one moment in time, all the tires are pointing straight ahead, right? And he sees one of those pillars in front of him. And he's Arnold Schwarzenegger, so he can turn the wheel really fast. So at literally the next instance in time, the front tire is going to be turned like that, right? So now we end up in our bottom picture. But right now, only the front is turned. Only the front has had time because we're at literally the next moment in time. So now we have some component of our force this way, right? What's that going to do? What does that create?
Drift. Slides, right? Like a slip.
Not
like the
in
rear
this case.
would yaw.
Yes,
Ooh,
you're
there
right.
you go.
Why would the rear yaw? What is this force doing? It's creating a torque, right?
Mm-hmm.
So at that first instant in time, only the front tire is generating force. And actually the car is going to rotate, not about the CG in this case, but about the rear tire. So the front is now trying to spin the car out, but our rear tire, if you think about like you're pushing, you have a block on the ground like we were talking about in the beginning, you can push on the block with some force, it's not going to slide, right? It takes a certain amount of force to cause the block to actually be in kinetic friction. So in this case, our rear tire is in static friction. So all that rotation is going to do is generate a slip angle in the rear, because now you're trying to twist the rear tire, but the rear tire is stuck to the ground same way as the front tire. So now you actually have a slip angle in the rear, and you have now this yaw angle beta. And I just want to point out, because this always seems to be confusing to aero people and other people on the team, just based on my experience over the years. When people like to think of a car yawed, they automatically assume that the car is like drifting or it's some like crazy extreme limit of grip event. But actually, anytime a car is cornering, it's going to have some yaw in it. It's not only in the extreme case where you're drifting or at some other extreme. So anytime the car's cornering, you're going to have yaw because of this torque caused by the front.
If I may for a second. So the way I would think about it, and I'd like your explanation, that component that Arash drew right here, right? We said the rear tire is in static friction. Well, the front tire is as well, but we're trying to rotate the car, right? Because Arnold just turned the wheel. If we go back to what Arash was saying when we were trying to explain torque, right? We have a wrench and we're pushing on the wrench. Well, the wrench in this case is from here to here, right? And what's happening is we're unscrewing the nut or whatever, and that produces this slip angle. Because we're twisting the body of the tire because it's connected to the frame. The rear tire anyway is connected rigidly to the frame, and that produces an angle because the contact patch wants to keep going the way it's going. So that produces that slip angle. So now we're able to have a slip angle in the front and the rear, and they both produce forces that turn the car.
Yeah. And once you have this like rotation in the rear, then the car goes to rotating about its center of gravity instead of the rear axle. So front and rear slip angles equal. The answer to that is it depends. And not always.
So you're getting ahead.
We'll get into that.
We'll get into that.
See, we know we did it right when the question's answer is on the next slide.
Yep.
So I have a question too. Maybe I don't know if it's the next slide or not. So slip, and when I hear slip angle, right? It's sort of a little bit of instability, right? Like
no.
Okay, so like it's the wrong. So the reason where I was going with it, well, when I hear slip or what I thought at least slip angle, you know, it's sort of sure it could be controlled, but it's out of the what was the continuous. But at the same time, it does induce.
What do you mean?
Like for example, when you're slipping, right? It's not like steering. So
okay, so let's clarify something here. If we talk about slip, we are talking about the difference in speed or angle between the bulk of the tire and the contact patch. Slip angle, slip ratio. If you want to talk about kinetic friction, I'll call that slide, or we can just call it kinetic friction.
Okay, I think I'm talking about what you guys are talking about and not the slide. All I'm trying to say is that, you know, this slip angle does induce some pros to the tires, right? But to a certain extent. So how would you want, so how, like, you know, that would create, for the little, from what little I know about tires, right? Like a higher lateral force.
Yeah.
But how do you know, you know, how do you control what that range is, or, you know, like.
So the driver controls.
Yeah, I was gonna say
the driver controls the front wheel angle, right?
Yeah.
So the driver turns the steering wheel to delta F. Using turns the wheel by delta F using the steering wheel. And this is something we glossed over on the tires. I mentioned it like once, but when we took my theoretical tire and we squished it to the table, right, and we rotated it, right, it wants to snap back to straight. You agree?
Mm-hmm. Makes sense.
Because you're stretching it.
Yep.
That produces a torque in the z-axis, right?
Mm-hmm.
And I don't really want to go into pneumatic trail and why it happens, but that torque changes as a function of slip angle. So the driver can actually feel when the tire goes from static to kinetic friction, depending on the way the tire is constructed and which tire it is.
Mm-hmm.
And their ability to feel that change in torque that's required to turn the tire allows them to keep the tire at a slip angle. So usually your average driver is going to turn the wheel until they start to feel the tire gets soft, or the wheel gets soft, right? And the wheel should get soft right around where it starts to go into kinetic friction. And that's what allows the driver to feel, when one of the ways the driver can feel the tire going from static to kinetic friction, if that makes sense.
So driver based.
The driver controls delta
Driver's
F.
the controller. Yeah.
Got it. Yeah.
Yeah.
Thank you.
There's a bunch of questions in the chat.
Tire sound, sometimes. Some
Yes,
tires don't
yeah.
make a sound before they reach the limit, or even after they reach the
Radials
limit.
often make more sound than bias plies.
Yeah. But definitely. But that also, Ashwin, comes down to the driver being the controller, because now instead of it being your like touch sensors, it's your ears.
Actually, and you also bring up an interesting point. So what is making that sound?
Yeah, that's a good question.
So what's making that sound is your tire, the rubber is in static friction, and it's like part of the rubber, let's say the front half of the contact patch is in static friction, and then it goes into kinetic friction, and that rapid change in displacement causes it to bounce, and it oscillates and makes a vibration in the air, which makes sound. Or the same thing happens and it vibrates the entire tire, which makes sound. But it's that loss of grip, that change from kinetic to static friction. And I don't mean the whole tire contact patch, I mean part of the contact patch. That change in friction is causing a bounce, which creates sound.
Yep. That's a really good question.
That is a great question.
Yeah.
Thank you.
Okay. So one other point here, because I know Jason's trying to do his suspension meeting. One other thing to note here.
This week, isn't it?
No, it's not.
Oh, whoops.
Yeah, yeah. So here's the CG of this car, right? And this is a car, I'm just going to say, we call this car a neutral steer car. And the CG here is equidistant from the front and rear axle. That means your rear axle to your CG is the same distance as your front axle to the CG. And if we think about something in steady state, so if you imagine this car going around in steady state, what does steady state mean? It means, in our case, there's no excess like moment or torque or anything, so your moments have to add up to 0. Yeah. So if you're drifting or anything, you would not be in steady state. You would be in some transient state if you're drifting. Well, you could be drifting in steady state.
You could be drifting in steady state.
Let's keep it simple.
Okay, you're right.
So in this case, like we said, we have our torque caused by the front wheel, the front tire, right? And that has some lever arm
LF
to the center of gravity, LF, right here.
Well, actually, the lever arm is shorter than LF because it's a component.
Well, the force still comes here.
I apologize.
Yeah.
You're correct.
Yeah.
You're correct.
Yeah, the force still comes here. So this has some lever arm to the CG. So like Cass mentioned, that's going to create a torque about the CG. So if we wanted to be in steady state and the rear tire had this lever arm where LR equals LF, how much force would it have to be? How much force would the rear tire have to produce to balance the front tire torque? Anybody? So do you guys know that torque equals force times distance, or your lever arm, right?
Sorry, Arash, could you repeat the question?
So you have you have a force from the front tire and you have a lever arm here, right?
There's chat.
Yeah, there's chat. So like Alex said, but to kind of clear up what you're saying, Cass, to make sure everyone understands it, you have a force and a lever arm from the front about the CG, right? And that's going to make a torque. And for you to be in steady state, that torque needs to be equal and opposite from the rear axle. So if you have the same lever arm in the rear, you're going to need to make the same force as the front from the rear tire to balance that out, like Alex said.
Yep.
That makes sense?
Yes.
Okay.
Do you want to make it more complicated or no?
No. Not right now.
Before we go down to the next slide?
I think that leads enough into the next slide.
You want to talk about
slip angle?
Delta slip?
Yeah, so in this case, since the CG is at the center, right? Your forces need to be balanced and you have the same normal load on each tire. Your front slip angle and your rear slip angle need to be the same to generate the same amount of force. Do you guys all agree with that? If all else is the same, they need to have the same slip angle to generate the same lateral force.
I don't.
Yes.
Okay.
Yeah, it makes sense.
Okay, cool. So now
we can talk about it later.
Yeah.
It depends on the radius of the corner.
Yes, it does. But let's just keep. I'm trying to just
Yeah,
lead
no,
into
I'm
the
with you.
next
I'm
slide.
with you. I think. Look, damn it, this thing just jumps. Okay.
Okay.
Fun stuff.
So, just like when people usually think about the car yawing as drifting. They like to think about understeer and oversteer, like these dramatic events at the limit, like you see with this like CHP dude just completely fucking up on the left, and this guy just spinning out into the bushes on the right. But oversteer and understeer, just like yaw, aren't things that only happen at the limit. They can happen anytime you're driving. So just keep in mind forces and moments from the last slide. So on the left, we have a car. We went from our 50-50 car to a car that has its center of gravity more towards the front axle now, right? So now let's say let's think about it this way. So the rear tire is going to be generating some lateral force, right? And now the rear tire has a longer lever arm to the CG than the front tire. So since this has a shorter lever arm and we want to be in equilibrium or in steady state, the front needs to react the same torque as the rear, right? So since the front has a shorter lever arm, what does that mean for the front tire force?
Greater.
It's going to need to be higher than the rear, right? And how do you generate more force in a tire?
Lateral force.
Lateral force. Yeah, you increase the slip angle, right? And increasing the slip angle in the front means you need to steer the tire more. So if we're talking about, yeah, to a point until you reach the limit, yeah. But so let's imagine we have some constant radius corner, right? And we have our 50-50 car from the previous slide. That can go around this corner with some steer angle, right? And it can make this radius. So now in this case, if we wanted to make the same radius corner with a car with a forward CG, we just said that we need to steer the front more so the front can make more slip angle and make more force. So to go around the same radius corner as the 50-50 car, you actually need to turn the wheel more in a car with a forward CG. And this is kind of what we're going to be calling, this is actually the definition of an understeer car. So now if you think for this car, if we try to go through this corner with the same steer angle as the 50-50 car, right? Now that means our front tire is not generating enough force to balance the rear, the moment caused by the rear. So if you think about now what the net torque is on the car, you have a force this way, you have a lever arm. So the net torque on the car is going to be like this. And what that's going to do is try and pull the front of the car out of the corner. So if you had the same steering angle as a 50-50 car, your corner radius is going to increase or you're going to understeer the corner. Does that make sense to anybody or to everybody? I hope it makes sense to somebody. But does that make sense to everybody? It does? Okay.
Yeah, thank
Cool.
you. That was pretty good.
So that's what we mean by understeer. It doesn't always have to be like this crazy dramatic event where you go straight into a wall and die. Your car can just be an understeer car just by design, and it's always going to understeer.
And I guess what you mean by going to the wall and die is where we talk about going from static to kinetic friction.
Yes, where your front tires just lose grip and your car doesn't turn anymore.
Yeah, both of these GIFs are kinetic friction because you can't really see this in static friction. You can feel it in the car. But what we are talking about here, we are talking about purely static friction.
Yes.
So you would require more steering angle to be at the same corner radius.
Yes. So now let's talk about the case where our center of gravity is closer to the rear than than being in the middle, right? So now it's closer to the rear axle, which is actually what our car is. We have about like 45% of the weight on the front axle, so like 55% on the rear, right? So this is kind of how our car is. So now we have a force from the rear tire, and now we have a shorter lever arm than the front, right? So what does that say about the force from the front? It has to be lower, right? And how do you generate a lower force in order to balance this moment? You steer less. So now you need less steering. So for this car, if we had that same radius corner that the 50/50 car went around, to make that same radius corner, you would have to steer less because now your front tire has a bigger lever arm, so it needs less force to balance the moment from the rear. Thanks, Trevin. So now, go ahead, dude.
Sorry. So yeah, so I actually, question. When you go into this kinetic, I guess, friction mode, right? Does at this point rotational velocity of the tire matter, or is it just based on mass, direction, and the initial inertia you have?
You mean how fast the tire's rotating?
Yeah, like if you just let go off the throttle versus if you hit the brakes. I mean, I guess it doesn't matter once you're in the kinetic phase, or does it?
So letting go of the throttle and hitting the brakes change your weight transfer, which can change how your car behaves.
But I thought once you're in the kinetic, right, none of that really matters too much because
it still matters.
Okay.
Right? The tires aren't like where you have grip, and you just fall off a cliff, right? You have some. I wish I can control the slides, but you have some room where you still have force after the limit, right? So you have this region where you have less force, but you can still produce some force, right?
I see.
So,
no, that makes sense.
So your oversteer and understeer are determined by speed, but they're like speed has an effect on them, I should say. But I don't want to like get into that.
No, that's fine. Thank you. Just clarified exactly what. Thank you. I think you have some other questions on the chat too.
Okay, cool.
Yes, sir.
Let me just finish my thought on this real quick before. So yeah, like for the oversteer car, like I said, for the same radius corner, you need less steering. So now if you had the same steering as a 50/50 car, now you're going to be turning a smaller radius corner because now you have the front is going to have a higher force. You're going to have a net moment in. So it's actually going to turn a smaller radius, or it's going to oversteer the corner.
That makes sense.
Does that make sense?
Yes, it does.
Okay.
Thank you, Raj.
Yeah.
Hey, Arash, I just thought of something else.
Go ahead.
So let's just put the CG aside.
Sure.
And so make it fixed. And can you go back to the first few slides where there was a graph for
the tires?
The tires.
Uh-huh.
This one?
Yeah, this one. The one with the blue and the green one.
Okay.
That one.
Yeah, this
okay.
one.
Yeah.
So on the graph, where would the position of the cases of understeering and oversteering be?
Okay, so if we're talking about non-kinetic friction, and we'll stick with the understeer case. So the rear slip angle is lower than the front slip angle for a given radius corner. So then your rear slip angle might be here and your front might be here. If the driver is right at the limit and not in kinetic friction, then they would be driving with the rear slip angle here and the front slip angle here. Right, but if they go any further, they're going to start going into kinetic friction on the front tire, right? And that may or may not be faster, right? Actually, I guess if we think about it theoretically, it would be fastest to drive right about here, where you're on both sides of the curve.
Oh,
actually, in this case, that would
understeery car.
That would cause you to. No, that would not be faster. You would want to be driving where your front tire is able to generate more force.
Oh, you do need that extra force. You're right.
Yeah,
you're right.
Because
then we're
now
plowing. Otherwise,
if you have equal force, you're going to have that moment from the rear tire causing pulling you out of the corner.
Yeah, so your front tire could maximally be here. Otherwise, your corner radius is going to increase, or you're going to plow out of the corner.
You're going to end up like that cop.
Yeah, in the gravel.
Where he belongs.
There was that you can't see it in the GIF, but there's a donut shop off to the side.
Yeah, exactly.
We don't have a cops in the audience.
It's fine. My father-in-law's a cop. He would laugh.
That's why. I see.
Yeah.
Okay. Is understeer and oversteer clear to everyone now? And also just the basic, very fundamentals of steady state stuff.
Yeah, and over and understeer can exist in kinetic friction, but the drawings in the bottom would be way different.
Yes.
And someone mentioned something about speed relationship, and I guess without getting too deep into it, one intuitive thing that I like to think about that everyone has experience with is how your car steers in a parking lot. So at very low speeds, right? You intuitively drive differently at low speeds so that you don't clip things, right? And that's because the rear cannot generate large slip angles when you're moving very slowly. It doesn't have time to produce the slip angles, or it doesn't have distance, I guess, in this case, to produce the slip angles to like move the rear of the car. So you go further before you turn the wheel really sharply, right? In order to go around things.
Okay. All right. Let's do some recap and then try and finish up.
Okay.
We've gone way over, but that's just VD life.
Yep.
Yeah.
No, this has been great. Thank you, guys.
I'm glad. I hope some of this stuff sticks at least, or it makes intuitive sense, or you understand how the car works better now, and you understand why aero works, or why you need shocks on a car, and how when you turn the tire, what's happening. Yeah.
Or you find a way to apply it to your particular section.
Now you can see why 911 is so oversteered too.
What?
Yeah.
For sure.
Okay. So, like we said, I mean, like not even as we said, as you guys have probably seen, VD and its modeling can be pretty complicated. And this is like as simple as we could try and make it. It only gets worse from here. Yeah, I actually had a full head of hair before I started on VD, and look at me now.
Yeah, Arash does all the work. I don't do shit. That's why I'm not bald.
So VD, so we try and model the behavior of the car and how the car reacts to different things in order to make it faster and easier to drive also, because you can do things, you can look at things like steering force, steering effort, steering angle needed, that will make it easier to drive. And like I mentioned before, you only want to make the model as complex as it has to be and not anymore. Otherwise, you're just either trying to flex or you like making your life harder for no reason. And make sure that you correlate your model to reality, so to try and prove some validity to it. One, to intuition, and two, to some sort of like test data or some physical actual data. Another thing, key takeaway, is that load transfer reduces the total force that your car can apply. Unless, I don't know if we talked about this, what's the case where you would want 100% load transfer?
We didn't talk about this. We can go back and talk about it.
There's one case where you would want 100% load transfer, and it's actually better.
Drag race.
What was that?
I think you said drag race, and you're right. So for our case, if you have a rear-wheel drive car and you're drag racing, you're only accelerating straight. Only the rear tires are providing forward thrust for the car. So you don't care how much weight is on the front tires. They're not really doing anything but making drag. Like, that slows you down. So you want to put all the load onto the rear. But yeah, otherwise, load transfer kind of sucks. Springs and dampers control how your car behaves to various road inputs, and dampers control the motion and kind of rate of motion and how the motion looks over bumps as you turn the wheel, basically anytime it's moving. And understeer and oversteer and yaw are not just like crazy things that happen at the limit, but they're a result of torque and force imbalance that causes a car to do different things compared to a neutral steer car.
I see some chat pings, but I can't click on them.
Yeah. I was just saying that's why in pro drag racing they have like the world's tiniest front tires and gigantic rear tires.
You can see it, and it's also, we talked about making the car longer. So if we go back to this, right, you can barely see the front tire at the beginning of the GIF, and it's way the hell out there, right? And that's so that the majority of the weight is on the rear tire because that's where they need it. And the front tires are very narrow because they don't have to turn the car much, and they just cause drag. The wider they are, the more drag they have.
Wouldn't that make the car kind of like flip upwards?
Well, so yes, and they actually run something called a wheelie bar, which is they have like the big drive tire, they have a small front tire. Go dragster looks like this. It's got these huge exhaust pipes and a fat wing. Perfect drag car. And they have this little trailing wheel off the back that keeps it from flipping over.
Oh, okay.
But they still want to keep their CG low because they actually don't want it. They don't want load going into this. They want it going into the tire. As much as possible, they try to keep the CG low so that they don't have a lot of load transfer. And the other thing is, even though the mass out here is very low, it's still so far out that it also helps to keep the vehicle from flipping over. But they do still run something called a wheelie bar to keep it from wheeling.
Okay.
Thank you. Thank all of you guys for taking your time to listen to us ramble also.
Dude, thank you guys. This has been
thank you.
amazing.
One more
thank you
thing,
both.
actually.
Really. Holy crap. I'm glad we recorded this.
So Arash just talked about where might we want 100% load transfer. We talked about acceleration only because we are a rear wheel drive car. If we had all wheel drive, we would want to be 50-50, right? So if we talked about braking, right? So what weight distribution do we want when we're braking? We want 50-50 after we hit the brakes, right? So before we hit the brakes, we might want it rearwards, right? So let's say we want 200 and 600 before we hit the brakes so that when we hit the brakes, it's 50-50, right? So let's say in braking, we want 25% front. In acceleration, we said we want 100% rear, so 0% front. In cornering, where do you think we want the center of gravity, front or back? Anybody?
Front, because then you can steer to your tires.
All I heard was front. Did you say a percentage?
I'm assuming, I don't know, 70% front. You won't really want a lot of front so you can steer.
Well, which tires steer the car?
The outer corner, whatever's the outer of the corner, whatever you're steering or driving.
No, but front to back, which tire steers the car?
Front steers the car.
The front steers the car? You sure? Sorry, which tires turn the car? Or cause it to produce lateral force? Or yaw, either way. Dang it.
Yaw? If you
Sorry,
talk
not
about
yaw,
yaw, I
lateral
would say the
force.
rear tires.
People are saying 50-50 in chat.
Okay. People are right.
Yes. Thank you, people.
For a square setup. Let me go back to my little drawing. Damn it. This thing is so laggy. Okay, so we had acceleration equals 0, 100. Braking equals 25, 75. cornering equals, hey, ABC, that's nice. 50, 50. So where do we want the CG? It sounds like an engineering trade-off.
Yeah, I don't know if it's just me, but
Huh? What'd you say? Cass, you cut off. He gave up.
We got stuff in the chat.
He gave up on us. The 50-50 was from before.
You guys hear me?
Yeah,
Now
we
we can hear
can,
you.
yeah.
Okay, sorry about that. I don't know what happened.
So what was your
Okay.
answer?
It wasn't 50-50, I'll tell you that. I heard 50-50 is the right answer, so now
It's not.
Well, so what's your, what do you think the ideal weight distribution is?
Yeah.
For turning?
No, for
No,
all cases,
overall.
for a vehicle.
Oh, for a vehicle. For a vehicle, I
For
think
a
the
race car.
deal is always 50-50. I
You
would
think the
still
ideal
think
load?
50-50.
So you
I
think
mean, I
we
guess
designed our car to
what
not
if we
be
just had
ideal?
a dragster? What if we were just doing drag races?
drag racing where you're just going straight,
Yeah.
then yeah, you want most of it rearwards because that's where all your moment is coming from, right?
Okay, so then it's not always 50-50. We have an XL event. So for XL, we might want 0-100.
You want to be slightly rearwards.
Ah, that's a good answer. How slightly? And how would you make that determination?
Just depends on the competition or whatever you're doing.
Sure. So we do Axel. So for Axel, we agree we want 0-100. Right? It's a drag race.
Okay.
So for skid pad, what is skid pad?
Skid pad mostly go in either one turn or the other turn. So you want to favor the, I guess, more front, I would say, in that case.
50-50.
No?
Think
50-50.
back to a force generation from tires and like diminishing returns and stuff. Yeah.
Okay, so then for autocross, what is autocross? It's a mixture of accelerating, braking, and cornering, right? But depending on the course, it may be mostly cornering or mostly cornering or mostly cornering. At least for the courses we do are mostly cornering. And the other thing is for accelerating, we only need 0-100 when we are grip limited. And because we are not able to do burnouts in every gear, like fifth gear, we can't do a burnout, then you don't need 0-100 anymore. Then you can cheat it forward and make it so that you can corner better, right? So because most of what we do in autocross and endurance is cornering, we would tend towards 50-50 with maybe a slight rearward bias to increase our performance in accelerating and braking.
I see.
If that makes sense to everybody.
Okay, I understand now. You see the overall. I guess you look at the overall and you choose something that favors the average.
Whatever will give us the most points, right?
Yeah.
So whatever makes us the fastest in each given event, right? We need the most points across all the events. That will give us the overall win. And because autocross and endurance are worth so many points, they get the biggest share.
Thank you for explaining that. I think you have another question on the chat.
I'd like to add one more dimension to the engineering trade-off study that you're talking about, Ross.
I'm trying to keep it simple, so.
I know. I don't want to overcomplicate it.
Yeah.
Maybe it's a topic for the next time you guys talk again.
Yeah.
But yeah, another dimension to add would be yaw, right?
Yes.
Yep. Yeah, it is.
Yeah.
So yeah, I mean, because the car, the like you said, the tracks are all different, and they may have more constant corners or constant straights, and not so many transients. But yeah, we do a lot of slaloms, right? And that's a lot of changes in direction. So the trade-off in terms of mass placement.
Yeah.
Yeah.
I agree. So yeah, it's all very complicated and wishy-washy. Anybody else? Or there's a bunch of chat.
There's some stuff going on in chat.
Are there any situations where having more weight in the front is useful? Sure. Not for our car, but sure. What if you have a Honda Civic and you want to do a drag race? Where do you want the weight? Because it's front wheel drive.
Because of front wheel drive?
Exactly. If it's front wheel drive, the weight in the rear does you no good. Oh, and one other thing that we glossed over in this model. So Arash mentioned that we have a drag force here, right? Because the tire's turned. In our case, we have to overcome that with an acceleration of, or not an acceleration, a drive torque inputted by the rear wheel, so that you end up with a counterbalancing force to make this, to keep a constant speed, right? In a rear wheel drive car. If we had a front wheel drive car, you would have to drive this forward such that this would end up going this way.
Mm-hmm.
Otherwise, you would lose speed. Any other questions before we kill it?
I don't know if you answered this one already, but there's one on the chat that says, what do you define as stability?
That was me asking Ashwin.
Oh, I didn't even see from who.
Yeah.
We didn't really get too much into stability. Stability is a tough animal.
But he was thinking if a slight forward weight bias would be more stable under acceleration, and I was asking what he defines as stability.
Sorry about that.
No, it's all good. It's good to think about too, though, for everybody.
Stability is important to think about.
Yeah, because people just say words like that and maybe don't think about what it means in terms of a car.
Mm-hmm. And we talked about it a little bit earlier with James when he was saying if we had a Mustang with 1 billion horsepower and we were going down a straightaway and the driver just mashed the throttle and they started doing a burnout,
there goes the crowd.
Would they be able to go straight? And the answer was, yeah, if everything was perfect.
Yeah.
But this is an inherently unstable system because if they have any sort of lateral force, right, then that will induce a slip angle, which will continue to increase the slip angle, and everything will become unstable.
Yeah.
So basically, the situation stability, in general terms, means that the situation does not return to where it started; it deviates to infinity or to some other value. So in this case, if you were doing this burnout and you induced a small slip angle, it would continue to grow and the car would spin, which we call instability.
Yeah.
If the car wanted to self-straighten, then it would be a stable system. In that case. And that's a whole bunch of other equations.
Yeah. And those equations change with speed. Or grow with speed. Depends on your arrow, but.
Well, thank you guys for asking questions.
Yeah.
And if there are any more questions and someone is afraid to ask them, they're welcome to hit me or Arash up on Slack. We'd love to answer them. We're here to provide you with knowledge as well as improve your ability to answer questions on your own, which is what we hope to pass on.
Thank you very much, guys. This was absolutely awesome and very informative. Thank
Anytime,
you.
man.
Yeah, thank you.
We can both talk about this stuff until we lose our voices, so.
Already accomplished.
Yeah.
Yeah.
You guys weren't kidding about getting confused on Saturday, man. I'll tell you that. Thank you.
Yeah, the more you know you don't know.
Yeah. Circle keeps on growing, man.
All right, guys.
All right, guys. Thank you.
Thank you. Appreciate your time.
Thanks, guys.
Okay, thank you.
Yeah. Good night.
Good night. Thank you, guys.